Okay. Hello, everyone. It's really a pleasure and honor to introduce one of the great scientists in the world, actually, Professor Andrei Rogash. He is one of the highly cited professors in in 2018, 19, and 20, and he is ranked number 51 over among the top 100 material scientists in the world, with more than 450 publications in the field of photonics and photonic materials. He actually graduated from Belarusian State University in Minsk, and he got his PhD also from the same university in 1995. Then he moved to Germany between 1995 to 2002 to work as a research scientist in the Institute of Physical Chemistry in the University of Hamburg. And between 2002 and 2009, he was the lead scientist in the photonics and optoelectronics group in the physics department and Center for Nanoscience at Ludwig Maximilians University in München, Germany. And also, since 2008, he's adjunct professor at the Trinity College in Dublin in Ireland. In 2009, he had the habilitation in physics at the Ludwig Maximilians University in München. And in 2009, since 2009, he's a professor in the Department of Physics and Material Science, City University of Hong Kong. And in 2010, he started the center. He's the founding director of the Center for the Functional Photonic at the same university in Hong Kong. He's also the associate editor in ACS Nano. And in 2012, since 2012, he is a chair professor of photonic materials at the Department of Physics. And since 2017, he's also another chair professor of photonic materials at the Department of Material Science and Engineering in the same university, with H-index 119 up to now. I don't know if after 2 days or something like this, it will be changed.
Today is 126, if you count these numbers, right? Yeah. So growing every week, right?
It is a change at 7 points since printing this paper. So it's a real pleasure and honor to introduce Professor Andrei Rogash to give us a presentation today about the carbon dots as a novel class of efficient luminophores. So, Professor Andrei, the mic is with you, and we are eager to listen to your great talk. Thank you so much.
Okay, Abu Bakr, thank you very much. So let me try to share my screen, then you tell me if you can see it.
Yeah, starting to come. Yes.
So I go to presentation mode.
Yes, this is slides only. Now it's okay. Yeah, it's fine.
Okay,
yes.
Good. Okay, now it's presentation mode, right?
Yes.
Okay. So first of all, I'm glad to be part of this workshop, and the reason why I am part of this workshop is that we actually had a joint project with Igor Krupa and his colleagues. We finished this project 3 years ago, maybe, right? Yeah. But we had very fruitful collaboration over 3 years' time, and your Qatar National Science Foundation provided us financial support. And essentially, we used to work on this topic, which I will present today: carbon dots, a novel class of efficient light-emitting materials. And this is also the reason why I pick up this topic to present today. I had the chance to listen to some of the talks which were ongoing today, and I mentioned they are very much applied, actually, and very much related maybe to economy of Qatar and to some very urgent needs for Qatar, like water desalination and all this kind of topics. Right? So my project here, which I will present, It is not Qatar specific, I would say, but it is devoted to light emitting materials, and you can imagine that they may be interested in for different purposes, like, for example, LEDs and displays, right? So I think you will still get it interesting, and you can learn something about what we call carbon dots, and just consider it as some particular kind of light emitting materials which may be useful for different reasons. And if we talk about applications of these materials, which I put here as my last point in my talk outline, we can actually use them for bio applications because they are biocompatible. So carbon is an environmentally benign material. We can use them for data encryption, so we can mark your Qatar money with this kind of hidden luminophore materials, if there is any need for that. We can use them for optical thermometry, and we can use them for solar concentrator. And what I did not mention here on this slide, but actually this was the topic of our project, we can use them for LEDs, for light emitting devices. So I will start my presentation from introducing you this kind of materials, and then I will talk about their synthesis and optical properties. And actually, the group of Igor and Peter, my another collaborator at Qatar University, you are guys chemists, right? You are maybe organic and polymer chemists. And what we also learned during our joint project is that sometimes when we make these nanoparticles, what we claim to be carbon dots, in fact, sometimes we produce molecular fluorophores, molecular dyes. So I would like to say some words about that during my presentation today. And then whatever we produce here, and actually then I will come back to carbon dots, to anorganic nanoparticles, we would like to have them emitting any possible visible colors. So we call them full color emitting materials, all the way from blue to the red. And I show you some examples of how we can make it. And then when we talk about anorganic nanoparticles, we pay attention to morphology control. So we can make them into spherical particles, and then we call them carbon dots. But then we can also make them elongated, like nanorods, or we can make them some other shapes. This is what I will also show you today. So when we talk about these so-called carbon dots, these are small spherical nanoparticles. This is why we call them dots. They are very small. They're typically less than 10 nanometer in size, most of the time 2 to 5 nanometer in size. And these are carbon nanoparticles, definitely. That is why we call them carbon dots. And if we check the XPS spectra, we can realize they have high oxygen content because at the surface they have OH groups or TOH groups. And in order to make these materials emit light, we actually need to dope them. So normally we pick up nitrogen, can also be sulfur or boron, to dope these carbon dots, and then they can emit light. And fortunately enough, the way how we make them is pretty simple, so we can take very cheap and available precursors, like this very classical combination. Citric acid is for carbon here, and amine, short chain amine, is for nitrogen. It's a doping source, right? And then we put them into autoclave, into aqueous solution or some organic solvents. We heat them up, and at temperatures like 200 to 300 degrees centigrade, roughly, we will carbonize these precursors, and then we make carbon dots. And if we look inside these carbon dots, actually, we will realize that their structure can be pretty complicated. I will talk about this more on my next slides. But if we put them on TEM grid, we can see some black spots here, which are nanoparticles. So we know they are really spherical nanoparticles, monodispersed in this case. If we go to high resolution TEM like here, we can realize that this particular particle is a piece of graphite. So this lattice plane belongs to graphite. But at the surface, there are always some functional groups, we call them. We are familiar about those from polymer chemistry, from organic chemistry. And in this case, as I told you already, this is mostly carbonyl groups. So here I place some pictures to talk a little bit more on how the synthesis occurs. So here we again take the precursor, pretty much what I told you before. We put them in water, these precursors can become charged, right? And then we apply temperature in an autoclave, normally we do it, or we apply microwave treatment. And then these two precursors will start to react to each other. And the first step here, we call it polymerization. So Igor should be very familiar with this kind of terminology and what will be formed here. And actually what is formed at this stage when temperature is not very high, some people stop here and they claim to make polymer dots. So this is already a nanoparticle. You can isolate them and you can treat them as nanoparticles. You can redisperse them in solvents and so on. And they contain out of polymers of this particular composition if we choose this particular precursors, right? But if we make carbon dots, we don't stop at this stage. We continue to heat them up for longer time or maybe at higher temperatures. And then here we talk about carbonization. So water will go away from this structure and this precursor framework, polymer framework, will get rid of water and organic nature, and it will become anorganic. So here we call them carbogenic dots, and this can be graphite, really, if they are crystallized. Or it could be amorphous carbon if they are not well crystallized. This is also possible. And then at the end of the day, here we get carbon dots, and we want them to emit light. And I will tell you in my next slides why do they emit light. But on the way to these carbon dots, so I talk a little bit here about terminology. If we stop at the stage of polymer, we call them polymer dots. And polymer dots can also emit light, by the way. If we continue our reaction, we make these carbon dot nanoparticles, and some people call them carbon quantum dots. And I always make a point here that this name is pretty wrong. So in literature, you can get some papers, quite many of them actually, which will tell you about carbon quantum dots. And if I see this kind of papers, I check them carefully. And most of the time, I will think these people don't understand what they're talking about. And the reason for that is that people like me who were working with quantum dots for decades. So if you talk about quantum dots like 2,6 semiconductor terbium telluride quantum dot, for example, so the name quantum dots means these particles have so-called size quantization effect, which means that if we change their size, we will change their band gap in the very fast approximation. For carbon dots, to be honest, this is very often not true, because the emission is not governed by the mechanism which we know from classical 2,6 semiconductor quantum dots. So for that reason, I always claim that these other two names, carbon dots, short acronym is CD, or carbon nanodots, which is also okay, then people call them CNDs, are better and more physically correct than carbon quantum dots. But actually, what we considered here, this kind of chemical synthesis, we call it bottom-up synthesis. This is what chemists do when they synthesize these materials from molecular precursors. We can also make them different way by top-down approach. And top-down means that we take, for example, graphite or nanotubes or even soot, and then we can oxidize them or exfoliate them or apply electrolysis treatment, and then we cut them into pieces. And then if this is a flat piece of material, which people call graphene quantum dot, so then this name is actually okay. because here the lateral dimension will determine their optical properties in their band gap. So the name graphene quantum dot, I find it completely fine. But this is, in ideal case, this is a flat structure, 2D material, what we know about graphene. Sometimes we can also make three-dimensional nanoparticles, and then they are carbon dots. And they eventually could be also called carbon quantum dots if they do have size quantization effect, if their band gap depends on size. But this is not always the case. So in my group, we started working on these materials back to in maybe 2013, 14. And I don't know if students realize it or not, but when we start working with new kind of materials, it always makes sense to write a review paper. Then we learn something, and then we can teach other people to something what we learned, right? And at the very beginning, when we start working on these materials, we wrote, for example, this review paper, Carbon Dots Emerging Light Emitters for Bioimaging, Cancer Therapy, and Optoelectronics. And this is actually a good illustration about envisaged application of carbon dots. Even 7 years ago, scientists already envisaged that they can be used for plenty of bio-related applications because they are non-toxic, right? But they could also be used for light-emitting diet. And a little bit later, we already started working on those. So we accumulated some knowledge about these materials. And we wrote another review, which is called here Optical Properties Effect of Doping of Luminescence Colloidal Carbon Dots. And when we touch this topic, and I will continue more along these lines in my presentation today, actually here there are some subtopics which are still very much up to date. So it's about nitrogen doping, it's about carbonization degree and how it influences optical properties of these materials. And this is also about the possibility of produce molecular fluorophores when we try to make carbon dots. So these keywords here, they are pretty much up to date, and I will discuss it in my presentation today. So this slide is very important actually because it summarizes optical properties of carbon dots. So for those of you who are familiar with optical properties of polymers or nanoparticles, so you will understand that we always take absorption spectra of these materials, and you can see here there are two well-pronounced peaks. And these peaks can be ascribed to n-pi star transition and to pi-pi star transition. So this is the language which is used by polymer chemists as well when they talk about conjugated polymers. And then there is some transition here at longer wavelengths, we call it Cephas state transition. So this is about absorption of these materials, but even more important is this picture here, which shows emission of carbon dots. And emission of carbon dots, will be one single peak. Typically, it is quite broad, and it is wavelength tunable one. And if you make photographs of these materials, you can also see that they emit light of different colors, like blue light, green light, orange light, right? But actually these photographs, they were taken from one and the same sample. These are three different cuvettes, but inside this is one and the same sample. We just excited them at different excitation wavelengths. And if we excite them at UV wavelengths, they will emit blue light. If we excite them at longer wavelengths, 450, they will emit green light. If we excite them at 530 nanometers, they will emit orange light. And this is something what is called excitation-dependent wavelength emission, which could be interesting property, useful property, or maybe not. It depends on application. Why do we get this kind of optical effect? For that, we go back to this structure here. And this is actually how people understand what are building blocks inside carbon dots which make them emit light. So you can see that they have so-called conjugated sp2 domains, which can be monolayers or two layers on top of each other, and there may be different number of benzene rings here. And this all these domains, they actually remind us something what we know from organic chemistry. I jump to my next slide here, and we call these building blocks pyrene or coronine molecules, right? Essentially, we can think about carbon dots like they're built up from multiple stacked B or three-layer complexes, which are constructed from pyrene or coronine-based building blocks. Many people look at carbon dots like they are made up from these building blocks. So this understanding can be well supported by theoretical calculations, by modeling. And this is what has been done by my colleagues in Czech Republic, in Olomouc, University of Olomouc. So they could reproduce absorption spectra very well when they did modeling for energy structure and optical spectra of carbon dots built up from these pyrene and coronine building blocks. So I go back to my previous slide now. And this build-up has also been confirmed experimentally in this paper, Fu et al., where I'm also a co-author. So this work was done by my previous group in Munich. And we say here that carbon dots is a unique fluorescent cocktail of polycyclic aromatic hydrocarbons. And these polycyclic aromatic hydrocarbons are nothing else than this kind of molecules, which are shown here inside this schematic picture for carbon dots. So when we excite this cocktail with different wavelengths, excitation wavelengths, we can preferentially excite smaller domains, and then they will emit blue light, or we can move on and excite bigger domains, and they will emit green light, or we can change the excitation wavelengths and excite the largest domain inside here, and then these materials will emit orange light. And there is nothing to do here with the actual size of carbon dot. For that reason, we should never call them carbon quantum dots in this way, because what counts here are actually sizes of these polycyclic aromatic hydrocarbons. Then the next question, of course, is can we control the sizes of these domains or not? In some cases we can. I will show you some examples on them. In some cases we cannot control them. And in some cases, actually, when people make carbon dots, they will produce aggregated molecular fluorophores. So this picture, this structure is complicated, right? Some people can call it messy. And it took people many years, actually, maybe 10 years up to now, to be able to bring some understanding in the structure of this particular materials. Okay, so this picture I already showed you. And my next point is that nitrogen doping is very important here, because nitrogen doping will trigger red shift of the emission of carbon dots. So most of the time when we make them, I come back here again, when people make carbon dots, they will make materials which emit blue light. And the photoluminescence quantum yield for this blue emission can be very high. 80% is easily possible. So this so-called photoluminescence quantum yield, I hope some of you know what is this quantity tells us. It means that from 100 photons will be used for excitation of this material, 80 photons will be re-emitted. So this is a very important characteristic of any light-emitting material. So initial papers on carbon dots, most of them, they reported blue-emitting particles. But definitely people want to make them emit any other colors. And in this story here, and this was also supported by theoretical modeling, we tell people that one way how to shift their spectra to longer wavelengths is to bring more and more nitrogen inside carbon dots. And actually, if nitrogen is graphitic, which means it is built into this graphitic lattice, like for the orange one and for the red emitting carbon dots, then it is better to shift the emission to longer wavelengths. And if nitrogen is at the border here, or there is very little graphitic nitrogen, then the emission color will be blue or green. But if we do so, we already receive what we want. We receive full color tunability for their emission. And another way how to realize red emissive carbon dots will be to rely on Cephas ligands, on Cephas attached moieties. Still they are nitrogen doped here. And this Cephas emission center, if they interact stronger, so we can compare this so-called free center or loosely bound center, like what is shown here, or tightly bound center, what is shown here. When we move from situation A to B to C, we will move the emission to red wavelengths as well. And this has also been shown theoretically by my colleagues from ITMO University in Russia. This kind of modeling is somehow complementary, but actually it's the next step to what was done before by my Czech colleagues, because here we can predict luminescence spectra of these materials as well. And here this was done in practice now. So coming away from purely theoretical calculations, what we did here, we made full color emissive carbon dots by taking these two particular precursor's, citric acid and urea, and we achieved different size of these luminescent domains inside carbon dots because we run those synthesis in different solvents. So when we made synthesis in water, we made smaller nanoparticles, and their polyaromatic domains were the smallest ones, so they emitted green light. And when we ran the synthesis in glycerol, we made bigger particles, they emitted green light. And when we ran the synthesis in DMF, we made the biggest particles and they emitted red light. But you can see from these nice photographs here that we can make any color in between as well. So this is really a beautiful example of full spectral tunability of emission color of these materials. So when we look at photoluminescence quantum hills here, blue emitting particles have highest numbers here, red emitting particles have lower one. 8% is kind of okay, right? I claimed you before that we can make 80% for blue emission, and this is indeed possible. 30+% is still a good number. So here, when we move to longer wavelengths, photoluminescence quantum yield drops, but this still allows us to make strongly emitting composites out of these materials when we put them into polymer matrix. And we can also make so-called down conversion LEDs out of these materials, which is shown here on the bottom row. And this is a good example of use for these materials for LED. So this can be used as a lamp, right? So different color tiny lamps. Or when we combine blue, green, and red color together, we can make LED which emit white light. And this is already a real life application because we can use them for lighting. We can make lamps out of these LEDs, and these lamps will provide us illumination of, for example, this kind of fruits here with a high quality white light. When we talk about high quality white light, we look at this so-called CRI index, and the closer this number is to 100, the higher quality is the white light. The more close it is to sunlight, which has CRI index of 100. Okay, so now I will talk about molecular fluorophores in the chemical synthesis of carbon dots. And I will recall that when we make these nanoparticles, we make use of organic chemistry, right? And organic chemists, they run this kind of reactions for hundreds of years. For example, these two German gentlemen, Berman and Hoffman, in 1884, they published the synthesis of citrazinic acid, which goes from exactly these two precursors, and then the product will be this A kind of product. We call it citrazinic acid. And citrazinic acid is a dye, it's a molecular fluorophore, So it emits blue light. Okay, and then depending on which kind of nitrogen precursor we will take here, and we always keep this carbon source, which is a citric acid. So then when we run this kind of reactions and when we look into organic chemistry books or old papers, we will realize we can make this different kind of molecules, which we call IPCA or TPCA or ATPCA, whatever name is. And these people here, Day-1 and his group in China, in 2015, they were actually the first who told our community, look, guys, when you claim that you make carbon dots, in fact, sometimes you make this organic molecule which is called IPCA, this one here. And this IPCA molecule will emit green light. This is not carbon nanoparticle what you make organic fluorophores. And in my group, we also came to the same conclusion. I will show you some of related slides very soon. We wrote this review paper, which I really recommend you to read if you are interested about this so-called molecular fluorophores on the research field of chemically synthesized carbon dots. So this picture is taken from that paper. We analyzed all possible synthetic pathways, which are summarized also here on this slide. We analyzed their optical properties, and we provided a lot of discussion related to this particular state. Of course, we also relied on our own studies, and one of the studies is illustrated here. So what we did here, again, we took one and the same carbon source, which is citric acid, and then we took 3 different amines. And depending on the amine here, then we run the reaction at one and the same condition, 200 degrees centigrade, 5 hours. This is a very classical kind of synthesis to carbonize those precursors. So then we get these dark solutions, and they did contain carbon particles all the time. So we saw them in PM. But on top of these carbonized particles, they also contain molecular fluorophores. And in this case, we could make IPCA molecule. In this case, we could make citrazinic acid molecule. And in the last case, we could make nothing, because this particular triethanol amine, it will not form any particular organic molecules at this reaction condition. And then all these samples emitted blue light, but photoluminescence quantum yield was pretty different. For this sample, it was the highest, 53%, and for bottom sample, it was the lowest, 7%. So it tells us that these carbon dots, which are formed here only, they are still emitting blue light, but their photoluminescence quantum yield is not very high. In 2 other cases, it is higher, and this was actually ascribed to the formation of molecular fluorophores. And of course, carbonization conditions here play a big role. This is something what we studied in another kind of study, which was reported here. So again, we took citrazinic acid, and then we ran reactions at 3 different temperatures, which is shown here by red numbers, 200, 140. And here we combine this citrazinic acid with graphene quantum dots. So we know that here there will be no any fluorophores formed. And then we made our samples, and what we studied here, it was actually photo bleaching of carbon dots as compared to molecular dyes. Because this is another advantage of carbon dots. Carbon dots are inorganic nanoparticles, so they are not supposed to photo bleach easier. They are very stable under continuous UV illumination. Molecular dyes can photo bleach very easily, and this is what we saw here. So when we look at this decay curve, how fast photoluminescence will disappear when we illuminate the samples with UV light, citrazinic acid is very vulnerable, right? So its emission will go down pretty fast. And for example, this so-called ECD200, the black dots here are pretty stable. So the emission still drops, but the remaining emission will stay long, and it will stay much longer, actually, which is not here. So all the carbon dot samples are much more stable than molecular dyes, which is a good message, right? So we can make sure that these nanoparticles, if we use them as light emitting materials, they will be stable against photobleaching. So now I will show you some more examples how we can make them in different settings. For example, here, this is an interesting kind of synthesis. We make green emitting carbon dots, again synthesized from citric acid and urea, but this is a solid state synthesis. So we don't use any solvent here. We make them in the walls of inflated foams. It's an interesting kind of idea, because when we mix urea and citric acid with calcium dichlorate, calcium dichlorate here is a kind of foam making material. So we put them under vacuum and then we heat them up under vacuum at different temperatures, and we form these light emitting foams. It's like a kind of powder, foam-like structure, and you see the color of emission is different. And if we take a piece of this powder and put it on TEM grid, we can find carbon dot nanoparticles. And you can also change the color because at lower temperatures they will be mostly smaller dots or maybe also organic fluorophores. And if we heat them at higher temperatures, they will carbonize completely and deliver us green emitting carbon dots, which we process, we dissolve them in solvents, we make fumes out of them, and so on. So another way how we change nanoparticle size for carbon dots, we use the so-called seeded growth method. So we start from very small nanoparticles, we call them seed. Their size is 1.6 nanometer. They emit blue light. So this is our starting material. Then we add urea and the polymer to this starting seed, and we heat them up. And depending in DMF solvent, so this synthesis is done in DMF solvent, and depending on how much precursor we use here, we will grow them bigger and bigger and bigger and bigger and bigger. So all these numbers here tell us the average size of these particles. So our biggest particles are 5.6 nanometer in diameter. And here the color of light will also change depending on size. Actually, we can call these carbon dots carbon quantum dots eventually. And you can see how emission will move from blue emitting materials to red emitting materials. And very interestingly, when we dry these solutions, we can get powders very easily, quite a lot of them. And these powders will have different color under sunlight. And if you put UV light to excite these colors, you can see they all emit different color of light. But this emission is so-called phosphorescence. Phosphorescence is different from photoluminescence because phosphorescence is a delay emission. So we illuminate them by UV light and then we switch UV light off. And even after hundreds of milliseconds or up to 1 second, these powders will still keep emission. We call it phosphorescence. And this can be very useful because it can have some applications in encoding information. So the physical origin for this phosphorescence is related to emission from so-called triplet states. So it's not the emission from singlet, what is shown here, but it's so-called intersystem crossing to triplet state, and then phosphorescence will go from here down to the ground state. And this is a strongly delayed process. That is why it takes few hundreds of milliseconds up to few seconds. So when we, for example, illuminate these materials, what you see here, under illumination, they will emit light, orange light, in this example, but even under UV light off, they will still emit color of light. And here, actually, we can encode it with some other symbols, not just 8888, but what is written here, 1501. And this gives us the base of so-called data encryption. using phosphorescence composites of this material. Another interesting property of carbon dots is that the emission depends on emission intensity depends on color, and this can be used for so-called nanothermometry. This was very interesting story which we published in ACS 2017. I don't have much time to go into details here because I see that my time is going away, right? So I will run through the remaining slides pretty fast. But the point here is that we can inject these carbon dots into the living cells, and then we can measure their so-called photoluminescence days, and we can determine lifetimes of this emission. So this is a photoluminescence. Lifetime here is a few tenths of to 10 nanoseconds. And this lifetime depends on temperature, which means that when we know lifetime, we will know the temperature of these cells. So we call it lifetime thermal sensing, and we don't need to put any thermometer into this cell culture, right? So we just look at the lifetime remotely, and then using this calibration curve, we can tell what was the temperature of the living tissue. And this may be very, very important for biological applications. So another very recent example of the use of carbon dots, which emit light in different colors, will be to use them for this so-called carbon dot-based tandem luminescent solar concentrator. This is a device which is essentially a few layers of coating on top of glass. And when we illuminate them by sunlight, these carbon dots will emit light depending on their size, for example. So this light can be blue or green or red, or combination of all of these lights when we put them on top of each other. And this light will be mostly coming out from the edge of this glass. This is called so-called solar concentrator. So it will collect light from the top, and it will concentrate it at the edge. And depending on what kind of carbon dots we put on top of this glass, we can get out different color of light, or we can get all these lights together. And then you will really get this kind of device which is shown on this photograph. And this is really a very nice potential application for these materials, because we can put this coating on the window maybe, and here we can attach solar cells to generate electricity. This is very interesting technology. So here I would like to report to you that we can also make carbon dots which emit infrared light. This is not trivial way how to make them, but we can do it. And if we can do it, we can use them also for biological labeling, because infrared light is able to penetrate through the skin, for example, of a living mouse. And it will come out as well. So this can be used for biolabeling, for example, of a cancer place for this mouse here. And how we did it? Essentially, we took carbon dots and we exfoliated them by so-called microwave-assisted exfoliation. Because these spherical carbon dots, actually, they have few layers of graphene. You can think about that way. And if we treat them using microwave, they will exfoliate. They will go apart a little bit. Or they can be evenly exfoliated completely. In order to do so, we make them emit infrared light. And this is exactly what we wanted to achieve by this treatment. So I still have a few slides here, and I know I have to finish my talk. So here I wanted to tell you that we can also control the shape of these materials. For example, if we synthesize carbon dots in so-called micelles, which are formed from this particular material, which we call POS, which is shown here. So these micelles are elongated. And when we carbonize our precursor inside these micelles, we will end up with elongated particles, which we call carbon nanorods. You can see a photograph here. And these particles will emit polarized light along this long axis, which is pretty interesting for some applications as well. And then what we also can do, we can get very crazy kind of morphology. Here you can see this kind of onion-like structure. This is something what we call carbon nanoroll, right? Schematic is here, and you can see from here, this really looks exactly like the scheme here. Right? So this is a multiple belt, which is rolled among itself. And actually, by unfolding these nanorolls, we can make long structures, which we call carbon nanobelts. It's a very interesting procedure. If you're somehow interested in this way of synthesis, please read our recent paper, which is cited here. So I arrived at my conclusions, and I introduced you this so-called chemically synthesized carbon dots, which is a new class of efficient light-emitting materials. And here I just cite some of review papers, which I did not show you during my slides today, but all of them, they are very recent, right? They're all from 2021. And if you are interested about molecular fluorophores, which we also form sometimes, please read this review in chemistry, in chem. If you are interested about full color carbon dots towards near-infrared part of the spectrums, you can read the recent review in small. And if you want to read more about applications of carbon dots, these are these two papers in nanomaterials and in advanced functional materials. And you can see all these papers published this year. So very, very recent review papers for those who are more interested in details. So this is my last slide. I wish to thank my people from my group. These are 3 people on this photograph with the faces put inside a sphere, right, a circle. Johan Schronk, Dr. Elena Ushakova, and Aaron Doring. And we have a plate of collaborators, in particular, Tara University. Peter and Igor, thank you very much. And my colleagues from University of Olomouc, Czech Republic, Songnan Chu from Macau, and Shue Bai from Jilin University in China. So we got funding for this from Hong Kong, Qatar, and Czech Republic. And thank you very much for your attention.
Thank you so much, Professor Andre. It's a very interesting talk, actually. I have some questions. So there is one question from RR, I don't know the name, but he or she says, how far away from real application are these carbon dots?
Depends which application we are talking about, right? So I claim that they can be used for these particular applications. And I think biolabeling and multiphoton imaging are pretty much close to real realization. And the reason for this is quite obvious because especially if we talk about infrared emitting materials and infrared windows of biological transparency, there are not too many other examples which are as good as carbon dots. I think biologists are very eager to use them in real setting. So for data encryption, we can do it. I'm not sure if someone did it in practice, but this is quite reliable and robust application as well. For optoelectronics, I think there are some other materials which are better than carbon dots. And this is also related to the fact that the emission is a bit too much broad. So for LEDs, we need a more narrow one. But when we talk about light, LEDs, it's also possible to use carbon dots. Eventually, some people may do it. And I also cited this very interesting application for solar concentrator. I'm not sure people will do it in practice, but I think the potential here is pretty decent from a simple fact that we can make this very large size coating, and this can be done easily in a very cheap way. And this can be done on Windows and can be used in real setting. Actually, the potential here is also pretty good.
For the solar concentrators, Dr. Andre, for the solar concentrators, this is for all the spectrum of light, or this is just only for typical wavelengths of the light or something like this?
We can tune the, solar concentrator, first of all, we need to collect solar spectrum, right?
Mhm.
And we can tune emission absorption of quantum carbon dots here over a pretty broad spectral range, so this can be adjusted. Then it depends which color of light you would like to get here at the edge. But this is really depending on some particular application you may think of here. And people normally thinking about getting maybe broad combination of light, what is shown here on this photograph, in order to attach here, for example, silicon solar cell panel. And this will help us to collect more light and to run this silicon panel more efficient.
Actually, solar application is very important as we do have a lot of sun here in Qatar. Anyway.
Yes, actually for Qatar this may be very much related, right? Huh?
Yes, yes, that's
Indeed,
true.
indeed.
One more question from Dr. Hani El Sayed from Germany. He's asking, do you see any future application of carbon dots in fuel cell devices as a stable support?
I think indeed. So we don't do it in our group, but indeed, for example, you can read this paper here, Advanced Functional Material 2021. So carbon dots, my talk today, it was focused on the light emitting properties most of the time, right? But many people use them as support, exactly what you're asking about. And some people use them as conducting materials in solar cells, which has nothing to do with light emission, but they can be used for this purpose as well. This is also a kind of support or filler material related to their conducting properties or just robust support materials. I think it's pretty possible.
I don't know if from the audience any more questions. I do have one question, Dr. Andre, regarding you for example, you mentioned something about you choose citric acid with amines.
Yeah.
How do you select these materials? I mean, what is the when you select the carbon source and the nitrogen source or oxygen source or sulfur or whatever? How do you make the design? How to select what you need for the application you target? You know.
Right. So design principles here are relatively straightforward, I would say. And the primary consideration has always been the availability and the cheap price of these two sources. For example, citric acid is a very simple kind of molecule. It is easy to get, it is cheap. It is soluble in water, for example, or some other particular solvents. So many people pick up this very basic molecule as a carbon source. Actually, carbon source can be anything. There used to be many papers about carbon dot synthesis where people will tell you your hair and bend them and you get carbon dots, right? Or take lemon juice or whatever juice you prefer to drink in Qatar and put it into autoclave and put some nitrogen source because you need nitrogen for doping and then you get carbon dots, right?
Mm-hmm.
So carbon dots can be acid, but somehow citric acid established itself as a very popular one, and I think one reason is that this is cheap and kind of standard.
Mm-hmm.
And for nitrogen doping, here it's a little bit more complicated, and here actually people have to pay attention what they pick up, because this is what you can see also and appreciate from this particular selection, right? So nitrogen molecules, typically they are short chain nitrogen molecules. They also can be cheap and easily available, but then eventually there will be these so-called concurrent reactions which will produce your organic fluorophores. And maybe you want to make them, maybe you don't want to make them. And if you don't want to make them, then, for example, you have to go for this particular triethanolamine, which will not give you any chance to make fluorophores, organic dyes. maybe you can well live with the fact that you will make them as well, because you just need something which will emit blue light with a high quantum yield, then it's okay to use ethylene diamine here, right?
Based on their absorption and emission of light, I mean, when they can absorb the light and becomes very hot. I mean, like it has some plasmonic.
No. There will be no such effect here. There is nothing what you refer to as plasmonic effects. I don't think. Maybe if you pump them very hot, they can become hot in real sense, right? Because there are some papers where people use them for phototherapy. But this will be a more exotic kind of pumping, right? And you have to design them on purpose. So Igor, I think Igor has some question.
Yeah, I just wanted to complete a question what Abu Bakr started. So we know that citric acid is the most common, and you said because it is cheap. So it means that the inherent structure or structure of molecule and the type of bonds is not crucial for final product, right? Or
it is crucial if you look into my slide here, right? Because this structure of this molecule, it will allow it to react with ethylene diamine and form this kind of conjugated ring, right?
Yeah, but your oxygen and another elements are lost, right? Because you have pure carbon, or this ratio of atoms in your original molecule, like hydrogen, oxygen, carbon, it's not conserved in your final product.
I think it also depends on how much you carbonize them, right? If you put them under very harsh carbonization condition, you will also carbonize the fluorophore itself. And then you end up with the carbonized particle anyway. So if you really want to make sure you make carbon dots at the end, you may want to treat them at even higher temperatures. Maybe many people use 250 or 270 degrees. And then the actual structure of this precursor does not matter, as you mentioned.
Because this is what I was always thinking when we worked together. How important is the source? I mean, the inherent internal structure of this. Because we wanted to study coal or many type of waste, but this is on the opposite. There are some impurities. So how can atoms can influence final signal?
If you treat them more gently, if you don't carbonize them to the end, then the structure is important because you may make these organic molecules. If you treat them at harsh conditions, at higher temperatures, at the end of the day, you will form carbon dots, carbonized, fully carbonized particle.
Oh, thanks.
I have one conceptual question from Dr. Yassin. He's asking, he's first thanking you for the informative presentation, and he's asking about the claim that some people claim that this is carbon quantum dots. He says, what is the minimum proof required to call it quantum carbon dots, especially for journals like ACS Nano, for example?
Maybe I go back here, right? So quantum dots means they show size quantization effect. It means their size will determine their band gap and it will determine their emission color. And on this example, I mentioned we can call them quantum dots, carbon quantum dots, if we know that inside these particles, they exist of a single domain, single conjugated domain. And you can see that this is a smaller particle, this is a bigger particle, and this is the biggest particle, right? And the emission color is different. That means their size will determine the emission color. So it looks that these particles, we can call them quantum dots. But there is still one important point here. We have to make sure that inside each and every particle, the size of this domain is pretty much the same, which means it extends over the whole volume of each particle, which could be the case, but it could also not be the case. Right? For example, maybe in this bigger particle, there is a mixture of domains. Right? So I draw it like that. It looks like there is one single continuous domain, but to be honest, we don't know exactly, right? And to answer this question, I mean, you cannot see it by any visualization, right? You cannot look at that by TM, right? You cannot do some other kind of analysis. You cannot look inside this particle. What you can do is kind of advanced optical spectroscopy. So you have to analyze their emission decays. You have to excite them at different wavelengths and check if the emission is wavelength dependent or not. Then you can actually say at the end if this is a single domain or not. It is possible to do, and some people do it. We know how to do it, but you have to pay attention to that.
Thank you so much. We have no more time, and I really thank Professor Andrei Rogash for the informative presentation on behalf of Qatar University and Texas A&M and all the audience. Actually, it has been a great pleasure to have you here, Dr. Andrei. Thank you so much, and hopefully we can meet again in Qatar or everywhere anyway. So thank you so much.
It will be my pleasure. It will be my pleasure. Thank you.
Thank you so
Thank
much.
you,
I
Andrei.
really appreciate it.
Okay. Bye-bye.
Thank you. Bye-bye. So now we will move to the next presentation, and it's also a pleasure and honor to introduce Professor Mohammed Saada Al-Deeb from Cairo University. Dr. Al-Deeb, he received his PhD from Cairo University in 1999 and was promoted to a full professor of physical chemistry in 2010. He received the prestigious GSPS Award postdoc fellowship for 2 years between 2001 and 2003 from Japan, and also the GSPS long-term invitation fellowship in 2007 in the Department of Electronic Chemistry at Tokyo Institute of Technology. In 2008, he was awarded the prestigious Alexander von Humboldt Fellowship to Ulm University, 115, Germany, for 21 months. He's the author of more than 115 international publications, which receives thousands of citations and H-index 30. The major research topic he is focusing on now is on electrocatalysis, energy conversion systems, wastewater treatment, and biodiesel production. Professor Saada will, please us today by delivering a presentation entitled "Tailor-Designed Nanoparticles-Based Electrocatalyst for Energy Conversion Applications." Professor Saada, the mic is with you, and we are all eager to hear to you. Thank you so much.
Thank you, Professor Abu Bakr, for the kind invitation to participate in this very important international event. Do you hear me, Dr. Abu Bakr?
Yes, we can hear you clearly, Dr. Muhammad. Yes,
okay.
Professor Muhammad. Yes.
Okay.
And we see the
Thank
presentation
you very much.
not in the show mode. We see the.
Yeah, my presentation. I mean, the sharing is clear for you or not?
Yes, we can see it. Yes, but not in the presentation mode. But we see the slides. Yes.
Okay.
Yes.
You mean like this?
Yes.
Okay.
Now it's okay.
So again, I'd like to thank you, Professor Abu Bakr, for the kind invitation to participate in this international event joined by Qatar University and Texas A&M University as well. It is my pleasure and honor actually to participate actually. So my presentation today entitled "Tailor-Designed Nanoparticle-Based Electrocatalysts for Energy Conversion Applications," and this is one of my research interests in my research group here in Cairo University, and in collaboration with my students also at the British University in Egypt. So I'm going to present some of our results. So the outline about fuel cells is sense and motivation, glycerol oxidation reaction at porous copper foams, and another application for formic acid oxidation at nanoparticle-based electrocatalysts. Then I'll end with conclusion. And as you all know that we are having some energy crisis for the traditional energy sources like fossil fuel-based energy sources like oil and gas. So we have to find some alternative for this, like solar energy, wind energy, and so on. Bioenergy also, and biomass and biofuel should contribute significantly to solve this problem and to meet the increasing demand for the energy needs due to the increase in economy and the industrialization and so on. Of these, fuel cells also are good alternatives for providing energy. And fuel cells, as you know, are chemoelectric engine that convert chemical energy stored in chemical bonds into, which is in the fuel, directly to electricity. This is opposite to the direct combustion of fuel by just converting it into carbon dioxide and oxygenated species. Then we can get only the thermal component of energy, but fuel cell we can get thermal component and electrical component as well. So the most famous clean energy source for fuel cell is the hydrogen oxygen fuel cell, and as you can see, we can just burn or oxidize hydrogen in presence of oxygen at cathode and the anode, so we can get water, heat, and electricity in fuel cell vehicles. Also, for currently, the gasoline is burned in the engines getting CO2 and water and heat and electricity as well. This one, if we can use this gasoline as a biofuel, like biodiesel, for example, or we can use this in fuel cell, we can get electricity component, which is useful one. And we can find that many fuels are existing, like formic acid, methanol, ethyl alcohol, glycerol. Actually, in our studies, we studied methanol as a fuel, formic acid, and ethylene glycol, and glycerol, as well as glucose. So fuel cells has high energy produced per unit mass of the fuel, high efficiency, no moving parts, no need for moving parts. It is only pumping of the fuel in the anodic compartment and air, for example, in the cathodic compartment, so we can get useful electricity output. So we can get also combined heat and power generation from fuel cell and the unlimited runtime. So we don't need to recharge or charging the fuel cell like batteries, because it is operating on a continuous mode of injection of fuel. Why we select glycerol ultimately? Because it is inflammable material, non-toxic, high boiling point, which allow easy handling and storage. This is opposite, of course, for hydrogen. Also, it has high theoretical energy density, as you see here, comparison between different fuels. And also, it is renewable fuel. It can be produced as a side product for biodiesel production. For example, from the triglyceride transesterification, we can produce biodiesel and the glycerol as a side product, which can be used here as a fuel in fuel cell. Also, it is low cost, and the production of value-added chemicals. We can oxidize glycerol into several value-added chemicals. Okay, we used actually some catalysts like porous material for glycerol electro-oxidation. We used some porous metallic layers like copper foams and the copper modified with nickel, and nickel foams also modified with some additives, and I'll show you some of our results. So here we can apply porous material for fuel cells electrolyzers to produce green hydrogen, which is a fashion of today, to produce green hydrogen from electrical energy sources, from renewable sources of electricity, and also we can convert the glycerol, as I said, into value-added chemicals. This is a simple comparison between fuel cell and electrolyzer. Very simply, we can say that for a fuel cell, we just inject the fuel here into the anode compartment and the air into the cathode compartment, and we get useful electricity output here. But for electrolysis, we apply potential to electro-oxidize the fuel and also to produce hydrogen gas at the cathode. In this case, we are converting the electrical energy into chemical energy stored in hydrogen, as well as we are converting glycerol into value-added materials. And here are the corresponding electrochemical equations with the corresponding potentials. And as you know, nowadays the fashion for green hydrogen, for the production of hydrogen from electrolysis of water. And here, this is a power source. This power source could be from solar, from wind, from any renewable energy source. So we can just directly convert water into hydrogen and oxygen, and we can use this hydrogen for energy storage. We can convert hydrogen into ammonia, for example. We can convert hydrogen into some liquid material, which is called liquid hydrogen carriers, for further use and transportation as well. So the point here is the catalytic layer, which is actually the main component in fuel cell and electrolyzers. Here we used some technique called dynamic hydrogen bubble template technique, and this technique is used to deposit porous metallic layer atop of substrate like copper foil. In this case, we produce intensive hydrogen production simultaneously with metal deposition. The produced gas bubbles here act as template for the metal deposition. So we ultimately can have some porous structures like this, and here these porous structures we can modify by deposition in presence of some additives, or we can further modify by doping with some other metals. Actually, these images, SEM images for copper foil, for copper foam formed on copper foil in presence of different additives and in presence of different nickel contents, for example. I'll show you some. This is a scheme for the electrooxidation, possible electrooxidation pathways for glycerol. And okay, we also use the same concept for the preparation of a good catalytic, good electrocatalyst for water splitting. And these are the reactions, all of you know this. So the experimental part here, actually, we prepared the copper foam atop of copper foil in presence of different additives, and also we prepare nickel foam on copper foil, also in presence of different additives. And I'm going to present only a little part of this presentation. Actually, this paper, this studies has been published in Journal of Electrochemical Society, Electrochemica Acta, International Journal of Hydrogen Energy, as well as Renewable Energy Journal, and also our SCC Advance. You can see from my list of publications. Okay, we use the traditional electrochemical potentiostat system like this, and this is the electrochemical cell we used for the preparation of the different catalyst layer. For part one, we prepared actually copper foam in presence of different additives. The main components of the copper deposition path is the copper sulfate and the sulfuric acid, and we just added some ammonium sulfate in one experiment. Another one, we added some potassium chloride and potassium bromide. The halogen here act as some absorbing anion on the surface, and we studied the effect on the morphology as well as the electrochemical active surface area of the prepared porous copper foam towards glycerol electrooxidation. And this is the other parts. In view of the time, I will skip this and I will present only the first part, which is the effect of additives on the copper foam prepared from acidic copper sulfate. And here you can see this is a typical CV for different films prepared in presence of different additives. And you can see film number 4 in presence of bromide shows the highest peaks for the redox pattern for copper, which indicates a successful deposition of copper foam atop of the substrate. Images are more or less similar, but the fine structure is a little bit different, and we cannot get any information from here except that we have some porous foam layer formed on the copper substrate, the planar copper substrate, and the index structure also confirms that we have copper and little bit oxygen on the top of the copper foil. XPS are more or less similar, except of the relative enrichment of copper to copper oxide ratios, which is of insignificant effect on the catalytic activity, as we will see later on. So glycerol electrooxidation here, the blue curve shows the CV for glycerol electrooxidation at film number 4, prepared in presence of bromide, while the green one in presence of chloride, the red one in presence of ammonium sulfate, and the black one in absence of any additive. We observed that a negative shift in the onset potential of glycerol oxidation, as well as increase in the peak current, which means that we have here different catalytic activity towards the same reaction under the same operating condition. By the way, in all cases, we have almost same loading of copper porous layer atop of the copper pair electrode. So glycerol electrooxidation, we here summarized the kinetic parameters or electrochemical parameters. The onset potential is shifted, which is the best one for film number 4, prepared in presence of bromide, as well as the current recorded at 0.35 volt is the highest here, also for the same film. Also the specific current, which is the current divided by unit mass milligram, is the highest also for film number 4, prepared in presence of iodide. And here this stability current time, also the same film, shows the highest current over 3 hours. We tried to estimate the electrochemical active surface area by measuring CV under different scan rates, and we can estimate that the highest surface area and the highest Faradic, the highest capacity Faradic value for film number 4, which is in line with the observed electrocatalytic activity, means that this film has a higher absorptivity for the spectator ions, so that it allows for higher oxidation current for glycerol electro oxidation. The effect of temperature here also, we estimated the activation energy, and we found that also film number 4 has lowest activation energy for the glycerol electrooxidation in alkaline medium. Also, we measured Tafel plots. So also this the blue one, which is film number 4, prepared in presence of bromide, shows the highest current, and more or less the Tafel slopes are the same. So no significant change in the rate determining step for glycerol electro oxidation. And here also this is electrochemical impedance spectroscopic measurement, and we also found the RCT for the film number 4 is the smallest, which indicate also that charge transfer is much supported at this electrode. As you can see here, we have here charge transfer resistance of 112, which is much less than the unmodified or the blank film, which is prepared in absence of any additive. The second part, let me move for the second part for formic acid oxidation. Also, we prepared some nanoparticle-based catalyst for formic acid oxidation, and all of you, I think, know about this introduction for formic acid. It is
we might have only 3 minutes left, so this is what we have. So I'm sorry.
Okay, Dr. Abu Bakr. Okay, let me go directly for the important part here, which is actually the enhancement of formic acid oxidation in presence of urea as a blending fuel. Here we can see that for this CV, we have here LSV for formic acid oxidation. For case A, just formic acid, solid line, this one, palladium nanoparticle deposited on glassy carbon, and in presence of urea, this one jumped up to this green one. So the presence of urea here enhances the oxidation of glycerol formic acid more than 3 times. This is not due to the oxidation of urea, because urea oxidation is not possible in this potential domain. As you can see, this blue line correspond for urea oxidation. So urea oxidation is not taking place at this potential domain, but the addition of urea to formic acid enhanced formic acid oxidation too much, as you can see. Here also this one on palladium modified with nickel oxide, you can see much more increase in the oxidation current of formic acid in presence of urea as well. So what is the role of urea here? We proposed some model. Actually here we proposed that urea act as antenna for formic acid, forming something like, as you see here, 8-membered ring atop the surface of the catalyst layer, which orient the CH bond down to the catalyst layer. So the scissoring of CH bond is visible and easy, so we can have CO2 directly from formic acid oxidation. Another proposal, we propose a linear polymeric chain, as you can see here. This linear polymeric chain also orient the formate anion CH bond towards the catalyst layer, so it is easy cut. And this is supported by some DFT calculations in which we found that the presence of urea stabilize the formate anion, and also it increases the dipole moment, which means that we can have some proper adsorption of formate anion atop the catalyst layer. So we propose this one, and this paper has been published in Renewable Energy Journal this year. And this is a discussion of the obtained results. Let me go to the conclusions directly. So we can say that additives greatly affect the morphology and activity of copper foam layers towards glycerol oxidation. Another conclusion for the presentation: the nano cobalt oxide and the nano gold act as catalytic mediator, facilitating formic acid oxidation and also facilitate carbon monoxide poisoning removal from the nano palladium layer. And most importantly, number 4 here, urea as a blending fuel played an essential role in enhancing catalytic activity towards formic acid oxidation by stabilizing the formate anion, forming 8-membered ring, supported by the DFT calculations, which facilitate the CH scissoring of formate anion to carbon dioxide. And thank you very much for your kind attention. And also, I appreciate again the kind invitation to participate in this event. Thank you, Professor Abu Bakr.
Thank you so much, Professor Muhammad. It's a pleasure and honor for us actually to have you. Thank you so much for accepting the invitation and give us this nice presentation. I have many questions actually, but the time is running out of me, so I have to move to the next speaker. So we will have the questions. I have a couple of questions here. Maybe I will forward them to Professor Eldeeb, and he will answer them.
My pleasure, Dr. Abu Bakr, inshallah. My pleasure. Thank you very much. Thank you.
Thank you, Muhammad, again. Let us move to the next, our next speaker, Dr. Bijandra Kumar from Elizabeth City State University. Dr. Bijandra is working as an assistant professor at Elizabeth City State University, which is a Constitution Institute of University of North Carolina system. Dr. Kumar, he has completed his PhD in Material Science and Engineering from Université Britannique Sud in France in 2010. Dr. Kumar's research interests actually is focusing on let me Dr. Bijandra has the key. Okay, Dr. Bijandra's research interest focus in developing nanomaterials based biomarker sensors, electrocatalytic reactions, electrochemical energy storage, e.g. metal ion and metal air batteries, and energy conversion like CO2 reduction, hydrogen evolution reaction, water splitting reaction systems, as well as design, synthesis, and characterization of advanced materials for energy-related applications. His research has been published in highly ranked journals, including Science, Nature, Energy and Environmental Sciences, and others. His current research is supported by Department of Energy and National Science Foundation and other international grants. And I had the pleasure to work also with him on one of the NPRP projects with Dr. Kishore. So, Dr. Bijandra, the mic is all yours, and we really honored and pleased to have you in this conference. And on behalf of Texas A&M and Qatar University, I'd like to thank you so much for accepting our invitation to present your talk here today. Thank you. The mic is all yours, and please share your presentation. Thank you.
Thank you, Dr. Abu Bakr. It's really great pleasure being here, and really appreciate and thank you very much for this opportunity. So I will skip a couple of slides, and because we have just only 20-minute presentation, so directly I will go to main work. So as we know, it's about renewable energy, and we know about renewable energy resources. And one of the best renewable energy resources is sun, because sun can provide, like within 1 hour, we can have at least energy for that will be okay for 1 year. But most of these energy, there is one problem. That problem is called intermittency. Like for example, in case of sun, during daytime, we have extensive energy, but during like night or like early in the morning or evening, we don't have really that much energy that we need. So what we need to do, we need to find a cost-effective storage system so we can store the energy when we have excessive energy, and then we can use whenever it's needed. So we know about lithium-ion batteries. They are one of the best in terms of like energy storage system, and we are widely using them. Like for examples, or your phone, cell phone, laptop, etc., etc. But the problem with these battery, they have really very low energy density. Like for example, compared to hydrogen or compared to this carbon-based fuel, they have really very low energy density. And the second issue is that though they are highly acceptable for many applications, but still we have some limited application for them. For example, we cannot use these batteries flying a plane. So still we need to, like design, like some other systems. So in that way, so we can use the solar energy or any renewable energy we can store in the form of chemical bonds. And the simple one is to produce hydrogen. So how we can produce hydrogen? Simple, we use water and to put electrode and apply the potential. So in that case, we can break this water molecule and we can produce hydrogen and oxygen. But problem is here, if you simply put two electrode, it needs a lot of energy because the thermodynamic potential for splitting water molecule is equal to 1.23 volt. But in practical application, depending on the catalyst, it can consume a lot of energy. So here we need to find a really very good catalyst that can break this molecule at low over potential. The second is storing these energy in the form of carbon-based fuel. That's really very great idea because here already we have established infrastructure and economy that's we use carbon-based fuel. So how we can store these renewable energy in the form of these carbon-based fuel? So there is a simple idea here. So what we can use carbon dioxide and water as a input, and then perform electrochemistry, and then we can produce carbon-based fuel, different type of product I will say here. And this process can be simply connected to renewable energy sources. So whatever energy we produce during the daytime or any time that we can use to perform this electrochemical reaction, and we can have this carbon-based product. But always developing energy technology is not easy, and there are many issues related to CO2 conversion. The first is product selectivity. Because when we perform electrochemical reaction, so carbon dioxide and water, they can react, and depending on number of electrons and protons, carbon dioxide can be converted to different types of product, like carbon monoxide, formic acid, methane, methanol, etc., etc. So, but we don't want to have that one. We want to have a process where we can selectively produce only one product. The second is energy efficiency. Again, like a splitting water molecule, we need a lot of energy to perform this reaction. So we need to find a catalyst that can perform this reaction without consuming too much energy. And the third is definitely, we don't want to have a low reduction rate, means we don't want to have a low production rate. And number four is definitely that's about the cost. So we want to find a cheap or inexpensive catalyst to perform this reaction. So as I mentioned, means CO2 electrochemical, during CO2 electrochemical reduction, we can have a different product. So for example, if you use a platinum as a catalyst, it doesn't perform any CO2 electrochemical reduction. Simply, we will have hydrogen as a product. In second case, when we use these silver or gold noble metal catalyst, they can convert carbon dioxide into the carbon monoxide. And they even means, like a need really very low potential, especially gold, that's a pretty good catalyst. But copper is a different type of catalyst that can provide a mixture of different carbon-based product. And there are another catalyst like tin or zinc. They can provide formic acid as a product from this reaction. So there are different products that we can gain. When we talk about CO2 electrochemical reduction process, so simply we need to know a couple of things. One is current density, the second is over potential, and the third is Faraday efficiency. Overpotential is the difference in the potential of thermodynamic potential and applied potential. So performance of a catalyst at given potential can be calculated by simply multiplying current density and Faraday efficiency. So in terms of to find an ideal catalyst, the catalyst must be in top left corner. It should have lower potential, high partial current density, high turnover frequency, and low cost. So a lot of work has been done. Means this type of work has been started initially by Dr. Hori, a Japanese scientist, in 1982 or 83, something like that. And since then, a lot of work has been done, but still, we are not able to find a great catalyst that can fulfill all these requirements. Though we are able to develop some catalyst that can produce carbon monoxide with really like 100% Faraday efficiency and even very low over potential. But for other carbon product, still there is a challenge, and people are working in this field to designing a new catalyst so we can produce these liquid fuel as well. So as material science is growing very fast and fast, so there are different type of catalysts that can be used for CO2 electrochemical conversion and hydrogen production. Definitely noble metals, they are the first priority, but they are really expensive. And recently developed TMDC catalyst, and afterwards means we also have MXene. There are maybe 1700 different type of MXene compound we can have. And again, there are metal organic framework. So depending on the chemistry, we can design a different type of catalyst and with different type of properties. And then we have these metal oxide and heteroatomic graphene. So today I will give you some example about TMDC and heteroatomic graphene and metal oxide, how really they work. So first is about carbon-based heteroatomic graphene for CO2 electrochemical conversion. So initially what we have done, we developed these carbon nanofiber. And when we tested these carbon nanofiber, they were really very great catalyst for CO2 electrochemical conversion. Like when we compare the current density and Faraday efficiency, so they have almost 100% Faraday efficiency for CO formation, and they have at least 4 to 5 times higher current density in compared to advanced AG nanoparticle. And then we come with the idea that when you introduce a nitrogen atom into this graphitic structure, that there is a difference into electronegativity of nitrogen atom and carbon atom. And due to that difference in electronegativity, these nitrogen atom can participate into the electrochemical reduction. Then we also run a stability test. We try to see means what type of nitrogen atom participate in the electrochemical reaction. So we did XPS analysis before and after. So what we have observed that there is no change in pyridinic nitrogen. So what does it mean? Because the catalyst is stable and there is no change in pyridinic nitrogen atom, so it means that's participating in the reaction, because if there is a pyridinic or quaternary nitrogen participate in the reaction, the amount of these nitrogen species is changing. So the performance of the catalyst should change, but that was not the case. So we propose that pyridinic nitrogen is the atom that participating in the reaction. And afterwards, people have done a lot of work in this field. They design a different type of catalyst, like graphene-based catalysts, vertical aligned carbon nanotube with nitrogen doping, and a lot of theoretical work has also been done. And it has been proved again that this is the pyridinic nitrogen that participate into the electrochemical reaction. So still there is some change, there is some challenges here, because when we have these graphitic carbon, so the content of nitrogen is really low. So one challenge is here, how we can enhance the nitrogen doping, because these pyridinic nitrogen, they are participating into the electrochemical reaction. So if we are able to increase the concentration of these atoms, then we can enhance the catalytic activity. The second is controlling type of doping, because only pyridinic nitrogen is mainly participating into the electrochemical reaction. So we don't want to have quaternary nitrogen or pyrolytic nitrogen. Another is conductivity. There is a trade-off, because when we do doping these carbon material, so we compromise with the conductivity. And the last definitely is selectivity, because in some case, due to impurities, we may have a different type of carbon product. The second is about TMDC. So we have a lot of kind of like compound here that come under the umbrella of TMDC. So in this case, we have one atom transition metal and second atom should be chalcogenide. So when it is chalcogenide, so it can be sulfur, Fe, and Te, and the transition metal can be like molybdenum, tungsten, or even gold, etc., etc. So they can have, like a TMDC material. So we try to investigate the CO2 electrochemical properties of this TMDC catalyst. So the first work that we have done, we used the bulk MOS2 and tested for CO2 electrochemical conversion. So what we have observed that bulk MOS2 have at least means kind of like 100 times higher current density in compared to bulk AZ, and at least means 6 to 7 times higher current density in compared to silver nanoparticle. And we are able to produce like a tunable mixture of carbon monoxide and hydrogen depending on the potential. And this mixture of carbon monoxide and hydrogen, that is called a syngas. And depending on the ratio of carbon monoxide and hydrogen, the syngas can be used for different applications. So when we try to just calculate means how efficient they are in comparison to other catalysts, so we compare the result with like a gold nanoparticle or copper nanoparticle or silver nanoparticle. So these bulk MOS2 showing higher performance in comparison to all these noble metal catalysts. So what does it mean? It means we can replace all these noble metal catalysts by TMDCs. So here just we tested the bulk MOS2. So we try to see means really from where this catalytic activity is coming. So we have done like a lot of characterization. So one simple conclusion is that these MOS2, they have a layered structure. So that's the intrinsic property of this TMDC. And these layered structure, when we just characterize their edges, they have metal atom on the edges. That is in this case molybdenum. And these molybdenum edge atom, they have a really high energy density and higher electron density in compared to silver nanoparticle or bulk silver. So due to higher density and easy exposure to electrochemical electrolyte, so it can perform better CO2 electrochemical reduction reaction. We also tested different type of other TMDC catalyst like MOS2, WS2, MOSC2, or WSC2 because they have higher kind of like electrochemical surface area, and additionally they have low work function. So low work function and higher electron density at each atom, that can provide means a better catalyst here. And when we test it like MOS2, MOSC2, WS2, WSC2, different type of catalyst. So WSCT catalyst was the best one, and it so at least means 1,000 times higher performance in comparison to noble metal catalyst. And the higher performance is attributed to these edge atom, which have low work function and higher energy density of electron. So that's why they are great catalyst in terms of like converting CO2. So another example about metal oxide. So here just I will provide an example of tin oxide. So when we have a tin oxide and when we do reduction process, so we have tiny oxide layer on tin. So that we say reduced tin oxide. So here we prepare 3 different type of catalysts, like for example, one is porous nanowire, and the second is simple nanowire. So when we test these catalysts for CO2 electrochemical conversion, so these porous tin nanowire, they provide higher current density, like for at least means 5 to 6 times higher in comparison to simple nanowire catalyst. So one question can come, because this porous nanowire, they have higher surface area in comparison to nanowire. So the higher catalytic activity may be just coming from the higher surface area. So we try to compare the experiment with a nanoparticle, tin nanoparticle. So here we can see, like in case of tin nanowire, the surface area is 6 meters square per gram, and here for porous, it's 35 meters per square per gram. And while for nanoparticle, it's 55 meters square per gram. So if it is the surface area, this nanoparticle must have some higher catalytic activity. But our results show that these porous nanowire, they have higher current density for formic acid production, even in comparison to this nanoparticle. So what does it mean? It means the higher CO2 electrochemical reduction performance is not attributed to just only surface area. It's attributed to the intrinsic catalytic property of this porous nanowire. And when we have done more characterization, so we just came with the conclusion that these porous nanowire, they have kind of like a defective structure where two different type of grain, they are merging and creating a lot of grain boundaries. And due to those grain boundaries, they have shown really high performance. And overall, when we compare the result with other catalysts, so the cathodic energy efficiency of this catalyst is really high at low potential. So that was another type of kind of like catalyst we can have. So in terms of designing catalyst for CO2 electrochemical reduction, definitely we think about overpotential selectivity and current density. And all these parameters can be controlled by controlling the intermediate binding energy and catalytic site density. And again, these two components, they can be tuned by different parameters, either by creating the vacancy or by doing the doping, or creating the defects like grain boundary, or creating a different type of like crystallinity and different type of step and terraces, or porosity, or 3D, different means option we do have here. So in terms of like to conclude it, so new catalyst beyond transition noble metals like TMDC, metal oxide, and these carbon-based material, they are really great and they are showing better performance in comparison to noble metal catalyst. And the hybrid structure can further tune the product selectivity and higher performance. And still there are some challenges remain, like understanding the properly reaction mechanism and then transferring this performance from lab scale to industrial scale. So here I would like to thank to different sources, and I have funding from DOE, NSF, and even I'm closely working with Qatar University with Dr. Abubakar. So thank you very much. If you guys have any question, let me know.
Thank you so much, Dr. Bijandra. Actually, it's a very interesting talk. Just for the time, just we'll have one question from Dr. Momin Islam from Dhaka University. He's asking, what is the stability of nitrogen-doped graphite towards oxygen evolution reaction in basic media?
I think it should be pretty good. I have not tested that, and I have not worked in that direction, but I think it should be pretty good, stable, depending on the applied potential, actually. Because if you are working really very at high potential, so definitely carbon can be oxidized easily, and especially when it is defective carbon.
Thank you so much. So we'll move to next presentation. Thank you so much again, Professor Bijandra. It is an honor and pleasure for us to have you here today. So thank you so much again.
Sure. Thank you.
Our next presentation will be delivered by Dr. Hani Sayed, and it will be entitled Oxygen Evolution Reaction Catalyst Stability Investigation using Rotating Disk Electrode Technique, a stability measure or an artifact. Dr. Hani Sayed, born in Cairo, and he graduated from Cairo University. He got his bachelor in chemistry degree, and he got his master and PhD from Canada. In 2006, he got his master from McMaster University, and in 2011, he got his PhD in physical chemistry from the University of Calgary, Canada. Dr. Sayed has been leading a research group at the Technical University of Munich, Germany from 2013 to 2020, where his research was focused on fuel cells and electrolyzers, electrocatalysts. Dr. Sayed is currently the head of Catalyst Technologies Department at Freudenberg Fuel Cell E-Power Systems in Munich, Germany. In his current position, Dr. Sayed leads 4 teams in the area of MEA development for fuel cell applications, and he has many awards. Actually, for example, he's got the Canada Government's NSERC Industrial R&D Fellowship, Alberta Energy Research Institute Lim Bolger Memorial Scholarship, Top Student Energy Researcher, Nanotechnology Alberta Ingenuity Student Scholarship, from Canada also, and the Energy and Environmental Systems Program Graduate Studentship Fellowships, for the scholarship, and he also has 2 teaching awards, Graduate Teaching Fellowship from Calgary University, and the 2004 DOW Canada Award for Excellence in Teaching. Dr. Hani, we are very honored and pleased to have you today. So the mic is with you, and we are all eager to listen to you. Thank you so much.
Dr. Abu Bakr, it is my pleasure to be here. Thank you so much to give me this such a wonderful opportunity. And I will just quickly try to get into the business and start sharing my screen. All right, so as Dr. Abu Bakr Abdullah already clarified that I was working at the Technical University of Munich for about 7 years, where I was leading a small research group under Professor Huber Gasteiger, who was a very well-known scientist for fuel cells and electrolysis and batteries as well. I'm currently the, let me just get a laser pointer here. So I'm currently the head of Catalyst Technologies department in the FFCPS. It's a fuel cell company in Munich, and that's only from the beginning of this year, from January this year. But the reason I'm still using TUM slides is that when I was at the Technical University, most of this work that I'm presenting, actually all of the work that I'm presenting today was done at the Technical University of Munich. So that's on all of the students, and everyone was basically from there. All right, so I will just jump into it right away, because already Dr. Uldeep already has covered something, but fuel cells, and also Dr. Kumar covered something with electrolysis. So I'm not gonna give any introduction about this, but I just want to quickly go into a very well-known technique that is currently used in the electrocatalyst field, which is called the rotating disk electrode. So the rotating disk electrode is a very well-established technique for oxygen reduction reaction, hydrogen oxidation reaction as well. So basically for fuel cell applications. And nowadays are people even trying to use the RDE to study different catalysts. And what happens is that they usually extrapolate the data or the results that they get from RDE to actual MEA, to actual devices, to actual fuel cell devices, which is possible sometimes. But what I would like to focus on today is the use of RDE, the use of rotating disk electrode for water splitting, specifically for oxygen evolution. So for those of you already who know, like, one of the best catalysts for oxygen evolution is iridium. Ruthenium is also very active, but it's not stable. So iridium-based catalysts are very active towards oxygen evolution reaction. And what you can basically see from this slide is that people not only try to use the RDE to detect or to determine the activity of oxygen evolution reaction, but they also use it to study the stability of the catalyst, of the OER catalyst. So I'm just showing here some examples. I'll have to try to be quick to stick to the time. So here basically one technique is or at least one method is called potential cycling. So you basically cycle the potential and see how the current decreases with the number of cycles. And this is already reported in literature. And during this reaction, what is happening is that oxygen is being evolved, but people use this to determine whether the catalyst is stable or not. And if the current decays fast, it means that the catalyst is not stable enough. And in this case, for example, you can conclude that the catalyst that has the red line, which is this catalyst here, is the most stable. So this is shown here from literature. Here's another example. And that's not the only method. You can also use a constant potential. So you can apply a constant potential, of course, in the active area region, where the region when the oxygen reduction, when the oxygen evolution reaction is taking place. And you can monitor how the current goes with time. And that's one example. And here's another example. And again, what you conclude out of this is that the red line, which stands for the specific catalyst, is that which is basically here, this catalyst here, is the most stable catalyst. Why? Because it doesn't really decay quickly, or according to this paper. Well, these are only two different techniques or two different methods. There's another method here, which is called the constant current. And this is, I would say, the dominating method in literature. So a lot of people working into the electrolysis area, they know that in order to use something that is more relevant to the application, it is better to apply constant potential and monitor how apply constant current and monitor how the potential changes with time. And this technique here has been used in literature for the last 10 years. And what I'm going to show you is that, unfortunately, this technique is not, or at least this method is not very reliable. But let me first of all just explain to you what exactly is happening there. So when you apply a constant current, and if the catalyst degradation is taking place, we will have to lose some of the active sites. So the number of active sites of the catalyst will decrease. And for that reason, the potential will have to increase in order to keep providing us with the constant current that we are asking the cell to provide. And as a result, you will see with time an increase in the potential, and all of a sudden you get this sudden increase indicating that the catalyst is not only slowly degrading, but now all of the catalyst is gone. So a lot of people are using this in literature, and this indicates a complete degradation of the catalyst. And here are some examples that show this from literature. So this is from 2016 and 2017 as well, and so on. So all of them basically use this technique. You apply a constant current, and whichever catalyst degrades faster, you will see that it's basically going through this sudden increase in the potential first, and the catalyst that is the most stable catalyst will stay there for a longer time, or at least it will make this potential jump, but it will do it at a very high, after like long time. Well, the problem with this technique is that we don't really think that this is what is really happening. Why is that? Because there's another group also here in Germany, in a small city called Erlangen. What they found is that if you use this technique and you try to predict the lifetime of a catalyst using a rotating disk electrode, I'm talking about an OER catalyst, so gas evolving electrode. They did this with the ruthenium catalyst, ruthenium oxide catalyst. And here is the stability when you apply this current here, and here is the stability level. This is only up to 2 to 3 days of ruthenium oxide if you apply specific conditions. And if you apply even more aggressive current, like aggressive conditions, like higher current, but in this case, the ruthenium oxide is not tested in a rotating disk electrode, but rather tested in a PEM electrolysis, so in an MEA, membrane electrode assembly configuration. What you see that the stability is much higher. It's about hundreds of days, hundreds of hours. So with respect to 3 hours, so now we're talking about 2, 3, 4 hours compared to tens of hours, maybe 30, 40, 50, 60 hours. So there must be some big difference between the two. So what I'm trying to say is, whatever catalyst you test in MEA configuration will last at least 2 orders of magnitude compared to the catalyst that you study using the RDE. So, and that's the conclusion here. So the OER catalyst stability in MEA is much larger compared to the RDE. So there was also the same group here came up with some explanation to this phenomena, and they basically showed that this is mostly due to the passivation of the backing electrode. So the backing electrode for them here is a substrate on which the catalyst layer is sitting. So they recommended not use glossy carbon, of course, and we all know this. If we're going to go to high potential, we should not. But they recommend to use, for example, gold or boron doped diamond. Why? Because it just takes much longer time for the catalyst to collapse. But even though if that's the case here, that's all RDE testing. So this is kind of the effect of substrate. But what happens is they can recommend this, they can and exclude, of course, the glossy carbon. But the issue is the inconsistency still exists, which is the RDE versus MEA. So in MEA, the catalyst can last for hundreds of hours, but in MEA, it can only last for 2-3 hours. So where this comes from? So we do have a hypothesis here, and our hypothesis is that we have always oxygen evolution, and the oxygen evolution, not only big bubbles, like what we call here the micro bubbles, but you can always form these micro bubbles that can form within the catalyst layer. So when you do an RD experiment, you are always keen to remove the bubbles that we basically can see, and these are the micro bubbles that we can remove by rotation. That's not a big issue. We believe that the micro bubbles that are inside the electrocatalyst layer, the porosity of the catalyst layer, cannot be even stirred out, and they have no motivation to get out of the electrocatalyst layer because outside is already oxygen saturated. So we really think that the accumulation of these microscopic oxygen bubbles are responsible of this phenomenon. So in order to show this, what we have done is we did a very simple experiment. We started this linear sweep voltammetry, of course, in the oxygen region, we're evolving oxygen, using an iridium ATO catalyst. This is a homemade catalyst. We have a paper that we published before about this, and you can see that when you keep cycling, within only 20 cycles, the current decreases. Of course, this cannot be really catalyst degradation. I mean, this will be really, really bad catalyst. But even though, what we did afterwards is that after these 20 cycles, we decided to purge the system with argon. Why? Because we think that the microscopic oxygen bubbles that are inside will only come out to the solution, to the electrolyte, if we purge with argon and remove the oxygen that is saturating the electrolyte. And this is basically what happened. So at the beginning, you have this black curve going from here to here, but after purging with argon, you start doing the linear polarization again, then you get a higher current. So where this comes from, you just simply emptied out the porosity, or at least partially the porosity of the catalyst layer. So this is basically our very first experiment that we did with this regard. So our conclusion is that the deactivation is at least partially due to shielding of oxygen evolution OER active sites. And larger fraction of activity is regained by allowing oxygen to diffuse out of the catalyst layer by purging with argon. Well, that was the first experiment. In order to prove that what is actually in literature is not really very accurate, what we did is the following. What we did is the typical experiment that is usually done there, which is applying a constant current and seeing how the potential increases with time. And you can see here that we applied a constant current using our iridium A2O catalyst. It's homemade, and we allowed the potential to increase by what is equivalent to Tafel slope. Tafel slope in this case 45 millivolt. And when the potential increases by 1 Tafel slope, this should correspond to a decrease or a degradation of the catalyst surface area by 90%, at least 90%. But the interesting part is we stopped the experiment, we bridged the system with argon, now there's no oxygen, and you find out that the CV is almost identical, and we did not really lose anything. And we continued. We went to the second Tafel slope, and as you can see here, again, with the second Tafel slope, we should have only 1% of the catalyst remaining. And in reality, we have about 50%. And you keep going all the way up to the jump. So this is the jump that is basically called in literature complete collapse of the catalyst. And in this case, of course, we still have the catalyst there, or at least we have about 40-45% of the catalyst there. So that's why we really believe that what is happening is just only blocking of the catalyst layer by oxygen bubbles. That's what we conclude. So at least that's not like everything, but we think it's significantly contributing. So let me just read out this out loud, is that the potential increase that we see here is mainly due to the shielding of oxygen evolution of the OER active sites being blocked. And this potential jump is most likely due to the complete shielding of the catalyst layer. So some catalyst degradation, of course, happens in this case, but this is basically induced because of the shielding. So the shielding is making the potential go to higher potential, and it's inducing degradation. So the shielding is not happening, the higher potential will not obtain, and the degradation will not even happen. So this is what's called kind of an artifact-induced degradation, what we call it. Well, let me just go to the second study, which is still very related. And in our first paper, when we published it, we were criticized that we did the work using our own homemade catalyst, and this catalyst maybe has some issues. So what we decided doing it is we wanted to do a comparison between RDE and MEA configuration. And that's basically everything you can use in literature. And not only this, we didn't use our iridium A2O catalyst, but we used a commercial catalyst that is kind of a benchmark catalyst from a company called Yomicor, which is iridium oxide on titanium oxide. And what we did in this experiment is that we started with applying a constant current. And of course, as similar to literature, what you find is the following. When this is again in RDE, so the potential keeps increasing slowly, and then we go through this potential jump. How long does it take? It took 9 days of measurement in RDE. And for those of you who are using RDE, I'm sure you know what it means to keep measuring this at 40 degrees, by the way. This measurement was done at 40 degrees for 9 days. It's a pain. But anyway, so we do this experiment. And of course, at the end here, you say, well, now potential jump means I have no catalyst. But the interesting part is, again, you purge with argon, and all of a sudden, you start again applying the same constant current. You potentially start right here. So the potential just didn't go up because you lost the catalyst, but you just shielded. You prevented the catalyst from seeing the electrolyte, and it starts normally from here, and so on. Now, what I would like to do now is that we applied, to show that what we also did is that we applied these identical conditions to RDE to membrane electrode assembly. And now what you can see is the following. The potential more or less start at the same point. These are basically identical conditions. And what you see is the potential of the MEA is not even increasing at all, indicating that whatever kind of phenomena, which we believe it's this microscopic oxygen accumulation, is happening in RDE to a significant extent, is most likely also happening in MEA, but to a much, much less extent. That's why the MEA potential does not really increase. Same thing. You stop, you do something similar to argon purging in MEA, and then the line is still the same. So it goes just straight. So there's no potential increase. And on top of this, after you finish the MEA testing, you find that the beginning of life and the end of life CVs are identical, meaning we did not lose any catalyst. So what is the conclusion here? The conclusion is if you take the same catalyst and you do RDE testing, the conclusion will be, oh yeah, this catalyst is not stable. In reality, if you do it in the actual device, as you can see here, it is actually stable. So that's why we wanted to warn the community that the use of RDE should not really easily be expanded to OER unless it is done carefully. And I won't be able to discuss this in this presentation, but there must be some precautions taken. Well, we did the same thing also, not only with the constant current, but we did it also for the constant potential. And now you can see again for the RDE experiment, on the same catalyst, under identical conditions, you apply also 40 degrees, you apply a constant potential, then it quickly goes down. And then you stop, you bridge with argon, you start up again. Well, if that was a catalyst degradation, it will never go up again by such amount of current. So again, this is indicating that this is only bubble shielding, and you can remove this effect at least partially. Well, we did the same thing for the MEA configuration, and here's the interesting thing. It really degrades as well, which means that we do have similar phenomenon also in case of the constant potential. So the current also decreases in case of the MEA. But the interesting part is during the reactivation, it starts basically on the same point. And what does that tell us is if we keep doing this experiment 10 times, the initial point would be almost the same, meaning the catalyst is stable. And all what we are seeing here is completely reversible phenomena, which we really think it is the microscopic bubbles. So now you can see this. Again, the conclusion from RDE is that's not a stable catalyst. From MEA, it's extremely stable catalyst. Last slide I have on this topic here is on the third method that also exists in literature is not only constant current, constant potential, but also potential cycling. So these are basically how the current decreases as a function of cycles. And this is the RD experiment. And you can see the potential goes down, the current goes down. And if you burge with argon, start from the beginning, then you get higher current, again indicating that the surface was somehow blocked with something temporarily. And we believe that these are the oxygen bubbles, and so on. And the interesting part, again, as I guess now you expect this, is for the MEA, you apply the constant, you do the potential cycling, it's more or less not really changing. And you do the regeneration, it starts from a higher value even. And then we'll go basically down in the same pathway, not really losing anything. So we put all these together, and this is basically the UI curve. And this is performance curve, or sometimes people are called the performance curve of electrolysis. Is you can see the beginning of life curve and end of test for chronoamperometry, for potential cycling, and for constant potential. All of them are on top of each other. What does that mean? It simply means that the catalyst that we tested in this study is basically super stable if you estimate the stability using an MEA. But if you take the catalyst and apply the identical conditions in RDE, the result is it's not a stable catalyst. So again, here's no catalyst degradation in MEA, but the catalyst significantly degrades in case of the RDE. Well, I think now I can conclude basically with this. I'm not going to read through this, but I just want to clarify is that we're not saying people should not use RDE. And we're not only specific on RDE. I think we're really talking in general about any liquid electrolyte method that we can use to study any gas evolving electrode. I'm not even specific about oxygen evolution, but any gas evolving electrode, specifically during the stability. Activity can be obtained, but the stability has to be treated really with careful caution. That's in our opinion. Well, at the end, as I said, this work was done at the Technical University of Munich. So I would like to work my supervisor, Professor Hubaka Staga, that worked with us for 7, mostly 8 years. And also would love to thank Mohammed and Alexandra, who now almost finished their PhD. And they did a lot of this work that I presented today. And of course, thank the whole group that I was part of. And thank you.
Thank you so much, Dr. Hani. It's very interesting, actually. As always, you always focus on the details. This is what I know about following your work, actually. Just one quick question, actually, we have. So because we don't have time, so what are the implications of this to regenerating performance for MEA stacks in industry? From Mr. Ahmed or Dr. Ahmed Badruddin.
What are the implications of this to regenerating performance of MEA stack industry? Well, we have regenerated this, at least in our case, in MEA, not in a stack, but for a single cell. And we have done this simply by some CVs in the cathodic direction. So, of course, we couldn't really burge with argon in case of an MEA. So the alternative is that we had to reduce the oxygen, which is in the form of oxygen bubbles, on the iridium catalyst. So basically oxygen reduction. We did this for a few cycles, and all of a sudden we obtained the whole performance from the very beginning. Yes.
Thank you, Dr. Hani.
No
we have been honored and pleased to have you here today. And on behalf of Texas A&M in Qatar and Qatar University, I'd like to thank you so much for accepting.
My pleasure. Thank you so much. My pleasure.
Thank you. So we'll move to our next prominent speaker, Dr. Ihab Elsawi. Dr. Ihab will talk to us today about designing materials and fuels blend to better understand the direct liquid fuel cell catalysis. Professor Elsawi received his bachelor and master degree from Al-Azhar University. Then he moved to the University of Calgary in Canada, where he received his PhD in physical chemistry. Dr. Elsawi received the Alberta Innovates a graduate student scholarship. It's called PhD Nano for his proposal for core shell nanoparticles and their fuel cells application. During his PhD, Dr. Assawi co-founded the University of Calgary Electrochemical Society student chapter. After his PhD, he joined Dr. Peter Pickup group at Memorial University, Canada as a postdoc fellow working on developing new anodes for direct formic acid fuel cells. After his fellowship, Dr. Assawi joined Dr. Bess group at University of Calgary again to lead research projects to develop ethanol electro-oxidation catalyst, electrochemical sensor, and redox flow batteries. Dr. Assawi co-authored many papers and book chapters and participated in several national and international conferences. He is a member of several professional organizations such as International Society of Electrochemistry, the Royal Society of Chemistry, the Electrochemical Society, and the Materials Research Society. And also the Electrochemical Society. And he serves as a reviewer for this organization too. Dr. Assawi's research interest is related to electrocatalysis, fuel cell energy conversion, and the storage devices. Also the electrochemical sensors, electrodeposition, and corrosion protection. In general, his material science is related to electrochemistry and electrochemical technologies. Dr. Ihab Assawi, we are very honored and pleased to have you today here. And the mic is with you, and we are eager to listen to you. Thank you so much. We can't hear you, Dr. Ihab. So most likely you are muted. Yes, you are muted. No, we can't hear you, Dr. Ihab. So.
Yes.
So now we lost the presentation.
I will fix that.
Okay. Thank you. Yeah, now it's coming. Yes.
Okay, thank you very much, Dr. Abubakr. And as you mentioned, this presentation will be related to better understanding of the catalyst or the reaction that's happening at the anode side of direct liquid fuel cells. So I will start with a quick introduction. Dr. Saada for sure introduced some of this for the fuel cells. So the world is depending on fossil fuels due to the very high demand for energy, specifically for the developed countries due to the increase in the number, and that demand for energy just causes loss of problems, starting from pollution and climate change problems, and also the centralized generation of electricity. It has combined with problems due to the power distribution, and for sure, because that's the oil and the fossil fuels are centralized in countries, this has caused even severe economical and society problems such as wars. So the need to replace the fossil fuels with a cleaner, more efficient, and energy conversion devices it's crucial. So a quick comparison between the current technologies with the internal combustion engine, as you can see here, we will find that it has a power output just in not covering the whole span of the whole range of the power output, and the efficiency is very low. However, if we look at the alternatives similar to the fuel cells or the fuel cell technology that's combined with gas turbine hybrid system, we could cover the whole power output system with the maximum possible efficiency. And the fuel cells usually it's a quite safe and clean technology, and because that wide range of power output is suitable for all the applications, starting from the portable devices until the actually the stationary applications. So because there is several types of fuel cells, I will not address all of these types for sure in my talk today. The fuel cells could be categorized according to the temperature, according to the membrane, according to the fuel. So my focus today is on the proton exchange membrane fuel cells, especially those running on running on liquid organic liquids as fuels. So this is a quick reminder of the principles. So we have the fuel fuel that's going in to the anode side, where the fuel is oxidized at the catalyst layer that's composed of gas diffusion layer and the catalyst layer. And then the proton moves through the membrane, going to the other side when the oxygen is reduced and give you water as a product. And this is the complete reaction that's going on. So this is the mechanism for all the majority of the fuels that's used in the direct liquid fuel cells, the methanol, formic acid, and ethanol. And as you could see, all of these fuels has carbon monoxide-like molecule formation as an intermediate during the oxidation. And these intermediates cause a very strong adsorption on the surface, hindering the further oxidation of the new fuels and block the surface for further oxidation. So in order to solve this problem, modifying the catalyst with the second metal, alloying the platinum or palladium with the second metal is one of the solutions. And that second metal usually affect the platinum catalytic activity through one or all of them of these following effects, which are the bifunctional effect, electronic effect, and strain effect. And I'll explain them in the next slide in details. So if the second metal has the ability to dissociate water at lower potential, so in this case, that oxygenated group at the surface will help oxidizing the carbon monoxide, and we call that the second metal enhance the catalytic activity through the bifunctional effect. However, if the second metal is changing the platinum electronic properties, so it's modifying the adsorption ability of the catalyst, so it's changing the carbon monoxide adsorption or weaken the carbon monoxide adsorption. However, at the same time, it's also will affect the absorption of the fuel, and therefore it may also hinder the catalytic activity of the catalyst. And the last is the strain effect. So if we are adding a second metal, so that has a different atom-atom distance, so that's also again affect the platinum-platinum atomic distance or the palladium-palladium atomic distance, and that may affect the adsorption and dehydrogenation of the fuel and converting it to the product. So in the case of alloy, as I mentioned, all these effects are mixed together. So I worked maybe almost for 5 or 6 years on designing core shell nanoparticles in order to separate the effect of the second metal from each other and see which one is dominant and which one is not dominant. And I will show you basically the strategy that I followed in order to do so. So if we have the core in here that has just put the pointer second. So if we have the core in here and then we have sub-monolayer of the shell on the top, so in this case the electronic effect on these atoms and the strain effect are constant. However, if we are changing the shell coverage, we are only changing the bifunctional effect as a second metal is exposed. However, if we just totally covering the metal with one monolayer of the platinum, so in this case we're removing the effect of the bifunctional effect and only we have electronic effect and strain effect. And further, if we just start to add more than one monolayer, so in this case we are buffering the electronic effect that's coming from the core electrons to the outermost active surface, and therefore we could basically by changing only the core size, we could control the strain effect. So I hope that I convinced you that all these effects will be mixed here. However, when we have a core shell structure with different coverage, controlled coverage, we will be able to basically distinguish between these effects. So this is all my publications or some of my publications on the core shell nanoparticles, in which we addressed in details the iridium core platinum shell, ruthenium platinum core shell, rhodium platinum core shell, and we applied for several fuels like formic acid, ethanol, and methanol. So just in today, I will just address in details the iridium platinum core shell and show you how basically we address the issue. So in order to synthesize these nanoparticles, we start with synthesizing iridium nanoparticles first. capped with BVB, and then adding cool down to room temperature, and then we're adding the platinum and allowing the platinum to grow at the surface of iridium. It's known in the literature, this method is basically making a pseudomorphic manner growth for the shell on the surface of platinum. On the surface of the core material. So our aim was to basically fully control the coverage of the iridium with platinum from 0 monolayer to 2 monolayers, as I showed in the previous slide. And we did that through calculations, assuming the core size and measuring the core size of 3 nanometer. And then once we know that the core size is 3 nanometer of iridium, we calculated how much platinum is needed to be added in this step in order to form a monolayer, how many of platinum is needed to be added in this step to form 2 monolayers, and then we start to control the coverage. So in this slide, I'm just showing that basically based on the WDS measurements, and the reason that we use WDS instead of EDS, because that platinum and iridium are very close to each other in the mass number. So the WDS is more accurate, and when we look for the theoretical iridium content based on the solution and the iridium content based on the WDS measurements, we found it's a straight line. That means that we have a full control on the composition of the nanoparticles. And in order to confirm this more, we did EDS on TEM on a single particle or a cluster of particles, and the composition came very close to the desired composition. And then we, for sure, for electrochemical measurements, we loaded this nanoparticles on carbon support, Vulcan carbon, and confirmed the loading using TGA in order to basically confirm that we have 10% metal loading on the surface. And then in order to basically explain if there is a strain effect or there is no strain effect that's going on during the growth of the platinum shell on the iridium, basically we did the XRD for all the prepared catalyst, and as we could see, the iridium XRD is just gradually changing to that of platinum, with increasing the coverage from sub-monolayer to about 2 monolayers. And basically that also decrease in the full widths and half maximum. It's indicating two things. One, maybe the iridium core is start to rearrange and become more crystalline and become the crystallized size increased, or that's only indicating the particle size increase. So we followed that with comparing the increase in crystallite size with the increase in the particle size from the TEM, and the increase in the particle size from the TEM matched very well with our theoretical calculation for the increase in the size according to the number of layers that we are putting on the iridium core. And that change in crystalline size, because it's matching with the trend, so we assume that there is no change in the crystallinity of the core while we are putting the shell on the surface. Due to the good match between the platinum and iridium, there is no mismatch that may cause strain. Also, another challenge was to basically characterize the surface of these nanoparticles, because iridium and platinum is very close and it's very hard to see them through the TEM. So we need to find a surface characteristic reaction that could distinguish between the presence of iridium or platinum and the surface. So we considered the first one, which is the hydrogen under potential deposition. In the case of iridium, the ratio between the weak absorbed hydrogen and strong absorbed hydrogen is about 3.9 to 1, while for the platinum it's about 1.3 to 1. So by tracking these changes and compare it with the theoretical value that we calculated due to the coverage, so we found that they are matching very well, except as at the 1.3 monolayer, which may be indicating that we don't have a complete, a perfect layer that has maybe some defects. And also we use the carbon monoxide stripping to track the surface nature. And as you could see, that's the iridium core before adding any monolayer, with just keep changing the surface coverage from sub-monolayer to complete one monolayer, the carbon monoxide stripping peak shifted toward that of platinum, with kind of a linear relation between the peak and the platinum coverage. And then basically with more than one monolayer, up to 2 monolayers, the platinum behaved as is the surface behaved as bulk platinum. So these electrochemical techniques, simple electrochemical techniques, was very efficient to determine the surface composition and allowed us not using any complex techniques. So after we did this characterization, we used our knowledge to explain the methanol oxidation activity of these iridium platinum core shell nanoparticles. So as a reminder, so when we go from submonolayer to monolayer, what we are doing is decreasing the bifunctional effect, but maintaining the electronic effect. And if we just adding more layers, so we are buffering the electronic effect and there is no strain effect. So because iridium and platinum has similar has some catalytic activity toward the methanol oxidation, so we had to instead of just seeing how they react separately, we want to see how they are enhancing each other, synergistic effect. So we calculated the expected current based on as if we are mixing them separately, and the surface is mixed separately, and as the measured current, which is integrating the synergistic effect, and we come up with a factor called the catalytic enhancement factor. So as you could see at low coverage here, so at low coverage, the catalytic enhancement factor was high, indicating that exposing the iridium to the solution will enhance the carbon monoxide oxidation, which is intermediate, and therefore enhance the catalytic activity of the platinum. However, once the coverage is increasing, the catalytic enhancement factor dropped, and that's happening at both low potential, where the carbon monoxide removal is a rate determining step, and at high potential, where the methanol dehydrogenation is the rate determining step. Also, we tested that at high temperature. The issue with the high temperature that the iridium regeneration of OH group is sluggish, so the bifunctional effects almost has no effect at high temperature, and this is because that the enhancement factor is almost constant, which means that's related to the electronic effect of the weak electronic effect of iridium on platinum. So I hope that these slides clearly shows that we could use the core shell structure to distinguish between the several effects or the mixed effects that may introduced by a second metal when we understand the catalyst. The second topic or the second part of my presentation today is related to the formic acid oxidation mechanism. So Dr. Saada mentioned in his presentation that blending formic acid with other fuels like ethanol, and Dr. Saada group has pioneer work in this side, when they are mixed formic acid with ethanol for oxidation on platinum. However, for formic acid oxidation, palladium is known.
We will have 3 more minutes.
Sure.
Thank you.
So formic acid, palladium is considered the highest active catalyst toward formic acid oxidation. So we said, okay, let's see how the ethanol may interrupt or enhance or interrupt the formic acid oxidation on palladium, and how that will gonna basically hinder the indirect pathway for the formic acid oxidation through the absorption, competing the absorption through this position with the molecule in here. So basically, the ethanol oxidation on palladium is inactive. That means there is no current will gonna come from ethanol oxidation. So all what will happen, it will be an enhancement effect or maybe inhibition effect. So we look at it. And then formic acid oxidation with increasing the concentration, what will happen is that the direct pathway, which is in the blue side in here, is almost constant. There is no change. However, when you keep increasing the concentration of formic acid, you are increasing the direct pathway, the indirect pathway, and the production of carbon monoxide. So when we start to add the ethanol to the highest concentration, that's basically have the highest indirect pathway, that's the ethanol directly inhibited the indirect pathway and without significantly affecting the direct pathway according to the CV. And then we put this in quantitative information by just deconvolute the peaks, and we compare the direct and the indirect current peak currents, and that, as you could see, with increasing the ethanol concentration, we have basically inhibited the indirect pathway. So in order to look at this closer, we took the first derivative of the cyclic voltammetry, and for basically an indirect pathway, what we expected to see is a harmonic shape, the green one. And for the direct, for the direct pathway, it's the green one, and for the indirect pathway is the red one. And when they are overlapping, they give us something similar to the blue one. So with increasing the concentration of formic acid, we shifted from the normal harmonic shape to another peak that's related to the indirect pathway. And once we added the ethanol, this peak that's related to the indirect pathway is compressed. So at this stage, we would just say, hey, we suppress the indirect pathway. This is a good blend, and it's perfect. However, that's not the case. CV is enough to say that the direct pathway is safe and the indirect pathway is only suppressed. So that wasn't the case. So we took the chronoamperometry at the small currents here in the direct pathway and try to test that using chronoamperometry. And what we found that with increasing the concentration of formic acid, the transition time decreased, even if we are doing it at low currents and low over potential, because that's the buildup of carbon monoxide. And this was the surprising figure in here, that's adding ethanol, not only inhibiting the direct pathway, but also inhibiting the direct pathway through the competitive absorption with the ethanol, with the formic acid, as I showed in the first cartoon. And that competition is very clear in the hydrogen under potential region, where we have the currents range up to 125. However, at high current, they become very similar, and the ethanol inhibition effect is just disappeared. So in these two studies, I just wanted to show that when we work in the field of fuel cells, better understanding of what's going on, even if we propose a new blend or we propose a new alloy, it's better to design the catalyst or the solution for better understanding, and then we move forward for looking at the higher catalytic activity. And thank you very much for listening. And I know most of you just want to see Cairo. You're like abroad for a long time. And thank you very much for this invitation, and thank you for listening. And I'm happy to answer your questions.
Thank you so much, Dr. Ihab. A very interesting presentation. And also I apologize because I didn't mention in the introduction that Dr. Ihab Sawi now is assistant professor at the university, at the American University in Cairo. So this is missed in the introduction. Thank you so much. We will keep the questions because we are back scheduled now. So we'll just go to the next speaker, Professor Muhammad Mu'min al-Islam from Dhaka University. Dr. Mu'min al-Islam is a professor at the Department of Chemistry, University of Dhaka. He completed his BSc and MSc from the same department, and then he got his PhD from the Electronic Chemistry Department at the Tokyo Institute of Technology, Japan. In 2004, he's in electrochemistry. He did postdoctoral research work for more than 4 years. His focus is on the designing material for supercapacitor, water splitting, and water treatment applications, in addition to atmospheric chemistry. Dr. Mu'min al-Islam is the author of 68 peer-reviewed papers in well-reputed international journals, one patent, in addition to one patent to his CV too. His first edited book, Trends in Polyaniline Research, and 5 book chapters have been published by different publishers. Dr. Islam is the editor of the Bangladesh Journal of Scientific Research, and is doing research under the sponsorship of many organizations like TWAS, Third World Academy of Science, and World Bank, and also the Ministry of Science and Technology, Ministry of Education, and Post Center at the Dhaka University. Dr. Islam is the acting as the Joint Secretary of the Bangladesh Association for Advancement of Science. Also, he received the Dean's Award in 2012, in addition to the Mombosho Scholarship, Young Research Grants, Alexander von Humboldt, etc. He is a life member of the Bangladesh Chemical Society, Bangladesh Crystallographic Association, and he is also, in addition to many other organizations, actually, and he visited Japan, Germany, UK, Malaysia, China, Saudi Arabia, India, and Bhutan. I'd like to, Dr. Momin Islam, the mic is with you, and we all got to listen to you, and we are pleased and honored to have you here today. Thanks for accepting the invitation on behalf of Qatar University and Texas A&M University in Qatar. So please go ahead. Thank you so much.
Thank you very much. I am very much happy to see you, my friend, previous friend, and also inviting me here. So can you hear me?
Yes, we can hear you clearly.
And can you hear the slides?
You can see the slides too.
See? Okay. Okay, thank you. So it is a really pleasure to me to meet you, and also for inviting me at these nice conferences. And I am hearing this session especially, and I saw that many scientists, polyisometalate-based catalyst for oxygen evolution reaction. So if there is any interruption, please let me know, because I feel that maybe there will be some interruption with this internet connectivity. So if you cannot see my slide, please just let me know. Then I can stop my video. Can you see? Can you hear me, Doctor?
Yes, we can hear you clearly, Doctor. Go ahead.
Okay. Okay. Thank you. So I am just summarizing these previous things that Dr. Bijanro and Dr. Hani, they are working on this oxygen evolution reaction, and Dr. Bijanro showed some catalyst, fantastic catalyst for oxygen evolution reaction, and Dr. Hani is trying to show that this there are some artifact with this oxygen evolution reaction due to this bubble formation on this electrode surface. So before going to this discussion, I would like to just to remind this, we have to work hard to meet this energy demand for this 9 billion people by 2050, and all of this energy is coming from our conventional fuels, and this of course pollute our environments, and it will finish by next 100 years. So for this switch to this new energy, of course we have to think about this energy storage system and distribution protocol. Here we can see this energy storage and impact on this environment. So we can easily see these primary sources, and these are secondary sources or storage system. These systems can pollute our environment, of course, but in case of renewable energy, if we harvest this sun energy from using some photovoltaic cells and wind energy, so we have to use this storage. So sometimes we have to use this kind of storage system, but best and decent way to get this clean energy is hydrogen. We know that for this we have to set up this electrolyzer. So our focus is this water splitting, and I will go very fundamental things, because my presentation is based on some special type catalyst we designed in our laboratory, and some catalysts are novel, and we work for this. So hydrogen is clean fuel, as we know, that it can be used combust to produce water, as well as we can use it as a fuel for fuels. So only thing is that we have to split water to form this hydrogen. So there are many ways we follow this electrochemical way. We know that this overpotential required to split water.
Manuel, can I just interrupt you? Your slide is not working. Can you just try to reshare it, please?
Not working?
No, we have it on the first slide yet.
Oh, really? So I can stop my video to ensure this connectivity, okay?
I think Dr. Islam, you may need just to share screen and then instead of just sharing the file, share screen and then put it on the presentation mode.
Yes, so I am now sharing only the screen, and so maybe problem with this connectivity, internet connectivity, as I mentioned.
Doctor, you can
Yeah, please.
then share again.
Okay, yeah, I am now trying to share again, but I'm now stopping this previous one, but it is not working. Okay, so oh, what's wrong with? You can hear me, right?
Doctor, if you want, you can send for me your PowerPoint. I can share it maybe from my laptop.
Yeah, please. It is
I'll
better.
send from my email now.
Sorry for this interruption. So by replying your emails, right? Can I
Yes,
reply
I'll send
you?
it to you by on the chat box now, my email.
Okay. Okay.
And no worry, doctor, this happens always, technology.
Oh, sorry. Chat box, you put it your email, so I just sending it. Maybe due to this slow internet connection, as far as I feel. I'm sorry.
So would you like to try to share again?
Yes. I am not
Here, I will
trying.
give you now a presenter. I will make you as a presenter. Can you please try again?
Yes, I just sent, and I am now trying also this. Okay. So to share this file again and screen share. So it is now working, and I already sent it. Okay.
Okay, thank you.
Is it visible? Is it visible to you? No.
No, not yet, Dr. Islam, no.
Maybe it is working. Sorry.
It's better to close all other applications in the computer.
Yeah. Yeah.
It's only the PowerPoint presentation available.
Yeah. I already closed all of this. Maybe due to this low bandwidth. Okay. It is evening now.
So it's
So
very heavy used.
yes, it's heavy. That's right. So can you see now? No.
No, not yet.
Oh, I was also thinking this. Maybe it may happen. I was wondering. So I already sent this file.
Okay.
Yeah, I think because it's heavy, I didn't receive it yet.
Oh, it could not be delivered. Just show me that. Okay. Way to deliver this.
Yes, now we can see, I think. Okay. Can you
Yeah.
can you activate the slideshow?
Yeah. Is it okay?
No, I think maybe it's better to click on one by one. That's maybe.
Yeah, it is now. It is showing that this slide mode here.
Slide 2 background. I can see now background.
Yeah,
Only.
but it's not in the slideshow. But anyway, there is no need for the slideshow. Can you click on the slides on the left side, Dr. Islam, to see if they will all respond or not?
Yeah, I am moving this slide. Okay, so maybe you cannot see the senses, right?
Yeah. Okay, we can see.
Yeah,
Good.
so it's better click on one slide by one slide, and that's better than the slideshow. The slideshow is not working properly.
Okay, so okay, so I will follow you. Okay, no problem.
Okay.
Yes, is it okay?
Yes.
No.
Yes.
Thank you,
Sorry.
Dr. Mo.
So I was talking about this point that water splitting needs some over potential, and this over potential comes from thermodynamic potential and anodic and cathodic over potential and ohmic over potential. Most important point is that in if we change this medium from acidic to basic, so in that case this hydrogen evolution over potential changes, and also this oxygen evolution over potential changes. So if we keep this reaction in acidic medium, highly acidic medium, then we can evolve this hydrogen without applying any potential. So only this kinetic hurdle and other energy needed for this oxygen evolution reaction. So our motivation is to design this catalyst. So usually researchers desire to. Can you see this slide?
Yes. Motivation.
Okay. Okay, sorry. So motivation is to design this catalyst by keeping this in mind that we have to say this design this catalyst with some good performance and stability, as well as some environmental friendliness, as well as this cost effectiveness. If you see this, that the abundance of this catalyst and the price, so this catalyst are highly high priced, but they have this high catalytic activity. On the other hand, these metals are abundant is very high and price is low. So we have been working with this type of catalyst, especially 3D block transition metals, as well as some carbon compounds, which is active functional carbon graphene, nitrogen doped graphite, as well as 3D block transition metal spinels, as well, and is a very uncommon polyoxometal. Recently, it has been using for water oxidation in the present research is going through this one, because it has a lot of possibilities for getting this opportunity, because it is this in this structure we can see that this octahedra is for this vanadium, niobidium, molybdenum, tungsten. We can sense this, and this central metal we can design this central metal by changing many of this metal, which is called counter ions of these polyanions, this big size of polyanions, and we can get this different kind of polyoxometallites by changing their preparation condition as well as composition. And we can also make this binary bimetallic by counter metallic polyoxometallate by changing this center metal by combination of this. So we have been trying to synthesize this induced or central metal polyoxometallate as well as this series. In fact, we have been working with this series. This is very much novel work in our laboratory, and other group also working with this polyoxometallate. So I will go through to discuss this result with aluminum polyoxometallate. We have synthesized all of these polyoxometallate given in these tables by using solution conversion method, which is very conventional method. In this case, very simply, we can synthesized using some glycerin fuel added in this system, and then this can be used. The precursor can be heated in a tube furnace at different environment, especially oxygen and nitrogen environment. We can get this catalyst, and here this definition of this catalyst is synthesized in our work. So aluminum means this counter cation, and POM polyoxymetalate, and this letter is number is defined this temperature at which this polyoxymetallic calcites. So some cases we can see these two types of counter cation here. So this means that two types mixing of two counter cations to get the benefit. And this catalyst is synthesized and then casted on this electrode surface with this film thickness like this, and used for water oxidation reaction or hydrogen splitting reaction. Here the example of this hydrogen oxygen evolution reaction, and this linear sigmotomogram and chronoamperometric tested for get the stability of this. And all of this, after this analyzing this, we summarize these results here, that we can get the onset potential and taper slope and taper plot, as well as a turnover frequency for oxygen evolution reaction. If we see this, the aluminum-based catalyst, this is chromium-based, and this is iron-based catalyst. Give among these aluminum-based catalysts give this low onset over potential, as well as low taper slope compared to other two, and as well as this high turnover frequency, indicating that this aluminum-based catalysts give high catalytic performance. And then we have been synthesizing, and we are now working with a second type of catalyst, in which aluminum is replaced partially to share with chromium, and polyoxymetalate prepared this to get the advantage of this catalyst. And we found that this aluminum-based catalyst, aluminum chromium bicatalyst, give this yield or have a percent of evolution of oxygen. So to understand the mechanism, then we did this further characterization, for example, ACM as with XPS, XRD, and also some reflectance analysis. We found that this gives this direct band with a direct indirect band with low band gap energy, and we found that this catalyst contains a high percent of tungsten 5 state. It has been known that this is very much important, and this is in fact unstable, because this tungsten 6 is stable than this tungsten 5. And in by our experiment, we could synthesize this tungsten 5 state with the help of aluminum. So it is known that this tungsten oxide, especially this cubic polyform, is thermodynamically unstable, but it is also previously reported that if we could replace this metal, the central metal, the aluminum, it can be possible to design this work. This speculation has been published in 1989, and recently we worked with this one, and we successfully get this stable compound for the first time, and we found that this tungsten 5 is very stable in this polyoxymetalate, and follow this published in the in this year. So I am now summarizing this, that as a counter catalyst, cation, aluminum support the formation of exceptionally stable tungsten 5 state in this polyoxymetalate. Aluminum polyoxymetalate, as OER catalyst, is washed in acidic solution by counter cation, for example, aluminum and chromium in polyoxymetalate enhance the OER catalysis. Plenty of works are to be carried out with this new family of aluminum-based polyoxymetalate as a promising catalyst. So, lastly, I have some acknowledgement with this, some funding agencies, and also these people who have been working and worked for this. This is Imran Hussein. He is now in Germany working for his PhD. And Imran Alit, he also worked for this work. And Tanvir and this three are now working with this project. So thank you very much. I am sorry for this interruption and due to this network connection.
Thank you so much, Professor Mognin Islam. I'm sorry, just for the matter of time, we have to move to the next presentation, our back schedule. So thank you so much. And on behalf of Qatar University and Texas A&M University in Qatar, also, I'd like to thank you again and for accepting this invitation and being with us here today, and looking forward to more contribution in the future. Thank you so much. And now let us move to the next speaker, Professor Ahmed Galal. Professor Ahmed Galal will talk to us today about the perovskite material for efficient hydrogen evolution reaction. Professor Ahmed Galal had his bachelor degree and master degree from the chemistry department of the Faculty of Science at Cairo University in Egypt. And in 1992, he got his PhD from the University of Cincinnati, Ohio, in the United States. He joined the chemistry department at Cairo University as assistant professor in 1992, and now he is a full professor at the same university. He had worked at several universities worldwide, actually. So he visited and worked in Ulm, Lagen, Ilmenau, and three universities in Germany, Cincinnati and Texas A&M universities in USA, University of Liverpool in UK, Polytechnic University of Turin in Italy, and United Arab Emirates and Kuwait universities in the GCC countries. Professor Galal served as a member of the Strategic Planning and Technical Support Center, which is a member of Board of Research for the Ministry of Higher Education and Scientific Research in Egypt. Also, he served as the Dean of the Faculty of Science, Cairo University, and as interim head of the Center of Hazardous and Environmental Mitigation of the university. Professor Galal earned several honors and awards, like the Graduate Fellowship Award, Quantum Chemical Corporation from USA, and the Fellowship Award of the Alexander von Humboldt Stiftung in Germany. Also, because actually it's very difficult to introduce Professor Galal. He has many achievements, actually. So I'm just skip, and he forgives me some of his achievements. He is editing and reviewing in many well-reputed journals. Actually, he's a member of the editorial board for Talanta Elsevier, and also is a member of the advisory board for the International Institute of Multifunctional Materials for Energy Conversion, DeWitt Loeb College of Engineering, Aerospace Engineering Department, and at Texas A&M University in Texas. Also, is a reviewer for the Royal Society of Chemistry, Applied Polymer Science, European Polymer Journal of Electrochemical Acta, Talanta, Material Science and Engineering B and C. Dr. Galal is focusing on the electrochemical sensors and nanomaterials, conducting polymers, and corrosion passivity of metals and alloys, in addition to environmental chemistry. Professor Galal, it's very hard to introduce you. Especially
I thank you very much, and I hope that we did not take the time out of the audiences as well. I hope that you are hearing me well, and the screen is on the display mode where everyone can see it.
Yeah, everything is fine.
Let me first thank you very much, Dr. Abu Bakr, and for the organizing committee, and for Qatar University, as well as Qatar University, Texas A&M in Qatar, and for this opportunity. And I would like to thank the previous speakers for their contribution that paved the whole way for me, in order not to repeat a lot of other information that might not be of interest to hear again. Let me go ahead and first start my first slide with the treasures. I call them the treasures. All the time, as a scientist, I would like to dig back in the history and in the past of the work that has been done previously. I would like to mention three of the most important ones that I all the time read over and over and over, and find new things to dig out of this kind of literature, but not to miss as well some other contributions that came out of the other listed here below scientists and many others that time and space will not allow me to mention about hydrogen evolution reaction that I'm going to talk today about using one of our homemade catalysts in that for that particular purpose. For some reason, during the month of October, I have been following all the time what is going on worldwide, but from many resources, I have been reading about all of these projects, mega projects, intended for the production of energy out of hydrogen and basically green hydrogen. As you may already know, that hydrogen is being produced mainly out of hydrocarbon fuel resources, and that's why people are now shifting towards green hydrogen. And the most important one is obviously electrolysis. Let me also, for some reason, I have some echo. Here is the very famous cyclic voltammogram that is being performed on platinum, polycrystalline platinum electrode in an acid medium, and 4 regions are being identified: the platinum oxidation for forming platinum oxide and oxyhydroxides, and the double layer region where no Faradaic activity is being observed, and then this large envelope for the hydrogen under potential deposition, and then we have the 4th region for hydrogen evolution reaction. This is the most important region here, where everybody is looking at this particular case. In some of the publications that has been coming out is the enhancement of the surface of platinum, especially single crystal ones, and for this purpose, the enhancement using transition metals and other oxyfoiling kind of ions would enhance the activity of hydrogen evolution, and the activity increases as the surface of the platinum is being modified, once by nickel and once by introducing something like lithium ions. So the introduction of some extrinsic materials over the surface will not lead to the so-called poisoning of the surface, but as well, on the contrary, will just do the opposite, will just enhance the performance by reducing first the overpotential needed for the hydrogen evolution and increasing the current density at a certain given potential. The mechanism has been also shown in this particular publication here, shown in Science, for the bifunctional mechanism, and some of the speakers have also pointed out this particular issue about the bifunctional mechanism. Of course, one would like to look at what Sergio Trassati has offered, and in this particular case, it's the famous volcano plot between the electron volt energy of the metal binding to hydrogen and the current density obtained, and this linear relation can also be deduced by comparing both the theoretical and the experimental work. Just going to the very basic, the mechanism that has been well agreed upon by all scientists working in the field, the 3 steps mechanism, starting by the Volmer and then the Hierofsky and then the Toffel step. Regardless of what the contradictions from different theories is actually telling us, we just came up with the conclusion that the hydrogen has to adsorb to the surface, and then the debate between the rate determining step, whether the diffusional one, the desorption one, or the combination. For our work, let me just go ahead and tackle the work that I would like to present for you today with some messages. We have prepared perovskitic materials, and the perovskitic materials are simply mixed oxides, and they have the general formula of AbO3 in its simplest form. However, binary metals like these can be between the transition and the alkaline and alkaline earth metals can be increased by doping the perovskite with more metals. And in this case, it will be a ternary and even a quaternary type of a mixed oxide. In our study so far, we have worked on binary mixed oxides and on tertiary and some quaternary work. I'm going to present for you today just the binary type of mixed oxides. One important fact about perovskites are two important messages. The first one is the tolerance factor from which the measurement of the crystal lattice is going to yield a stable perovskite. And the second message is the catalytic origin that is played by the perovskite, which is the oxygen deficiency. So when you have more than one metal in the crystal lattice, they are all the time competing with the oxygen acquisition in the crystal. And that's why this oxygen deficiency would allow more of the freedom of the valence electrons of the metal centers to contribute to the electron transfer process. Similar volcano diagrams have been constructed, and in this case, we can see a lot of variations between binary to tertiary and to others, and many combinatory mixed oxides. For further information, you can just look at these particular two important publications to look more further about the structure and catalytic ability relationship. What did we do experimentally? We have tried to prepare the perovskite in a green approach, or a greener approach. The reason for that is, in order to prepare a well-defined crystalline and pure form of a perovskite, one need to perform a simple chemical reaction and as well to perform a calcination step. And the calcination step normally needs a huge amount of energy. In this particular work, instead of using the calcination step, we just use microwave irradiation. And at the same time, in order to transform the single oxides into a mixed oxide perovskite, we used graphene oxide as a fuel. Graphene oxide will be reduced also at the same time while the perovskite is being formed, and it will be reduced to the reduced graphene oxide form. And from that, we used this particular mix or composite material for testing it for hydrogen evolution reaction and compare it to the literature. We have confirmed the formation of the reduced graphene oxide from the XRD pattern and the formation of the corresponding perovskite as well. This slide here shows you the effect of the amount of graphene oxide used as a fuel. And as you can see, the most important distinct peak here is being increased as the amount of graphene oxide is reduced, which means that the graphene oxide has to be stoichiometrically used in order to obtain the desired confirmed crystalline structure. Now, the effect of irradiation time has been also tested, and we have concluded that between 5 minutes and 25 minutes irradiation is completely enough to produce the perovskite, and we compared that to the firing of the corresponding perovskite. Some other evidences for the formation of the reduced graphene oxide was being conducted by running just simply the Raman spectra in order to identify the formation of the reduced graphene oxide by just taking the ratio between the G and D bands in the Raman spectra. And this spectra here is for the lanthanum iron oxide perovskite, and this is for the mixture between the two in the form of the composite. These are the scanning electron microscopes and the corresponding EDX spectra, and we noticed that the lanthanum iron oxide, which is from the XRD measurements, were identified between 27 and 31 nanometer in average size. And we have seen that it was wrapped by the reduced graphene oxide, with some of the lanthanum oxide, lanthanum iron oxide being identified over the surface. High resolution transmission electron microscopes as well identified for us the structure, and we have also performed some selected area electron diffraction in order to confirm the formation of the crystalline pattern of the lanthanum iron oxide. From the XPS, we have also confirmed from the spectra of carbon, the spectra of oxygen, we confirmed the formation of the reduced graphene oxide by comparing the ratio of the carbon single, carbon double bond, deconvoluted carbon spectrum, as well as oxygen spectrum. And from the measurement of the lanthanum iron oxide spectra, we have found that lanthanum 3+ is the predominant one, and the iron 2 as well. Now to the linear sweep voltammograms and the TOEFL plots. I'm sorry, I hear a lot of echo in the background. Yes.
We don't have any problem.
The voice
Okay.
is
Okay. I think the microphones are open, so I hear a lot of echo. Okay. Now I will just go on. The linear sweep voltammograms shows an important fact here. Look at this green line here for the linear sweep. This is for the lanthanum iron oxide RGO compared to the lanthanum iron alone and the RGO alone. Now, when we first tried to publish this work, the comment came from both reviewers. It will be okay if it is believed to be real. So we had the first rejection without any further comments, because it was not accepted to have such a shift beyond the zero potential for the onset of the hydrogen evolution. We have tried to confirm that there is no impurity present in the samples over the surface of the electrode, and to purify the electrolyte as much as we can. So we compared our results by running the experiments in sulfuric acid as well as in perchloric acid. This particular one shows the same experiment, but when adopting the catalysts over carbon-paste electrodes, just to test the performance of the catalyst over different surfaces. In order just to examine the stability of the catalyst, we run the experiment for about 50 cycles, and we then at each time we take the electrode out and then we run it for a linear sweep to compare the first and the 50th run. And we have also conducted the effect of scan rate just to examine whether we have a diffusional process at the interface. This comparison here compares the different surfaces of the onset of potential, and as you can see here, a positive value for this particular catalyst, but surprisingly enough, with a very high TOEFL slope, but with a reasonable exchange current density, and also with the current density at zero potential, and at about 0.1 volt, and at 10 milliampere, what was the amount of currents obtained, just for the comparison of the performance. We also went further by comparing the catalyst that we used, that you can find at the bottom here, with different catalysts and surfaces used in the literature. We found that the reasonable amount of current density obtained and the values of onset of potentials for the hydrogen evolution was completely an interesting result. As I told you that we have tried to run the experiment in perchloric acid, and we have found exactly about the same result. Now, to conclude with almost the last slide, we have tested the catalysts at different applied potentials for long extended period of times, and we have found that we have a steady performance with almost no change in the current density obtained. We compared our work to other catalysts in the literature, and we have found again that the work that we have done with the catalyst is showing a very good thermodynamic favored electrochemical conversion process. In conclusion, we have introduced a one-pot facile green and energy efficient method for the preparation of a composite of a perovskite and a reduced graphene oxide. No need to use a high temperature for the calcination of the perovskite to obtain it in the pure form. And it was also a one direct transformation of the graphene oxide into reduced graphene oxide. The as prepared lanthanum iron oxide was confirmed to be in the nano size, and it was in a pure form. The prepared composite showed a noticeable catalytic activity for the hydrogen evolution reaction with an exchange current density of 3.65 milliampere per centimeter square. We have different catalysts prepared currently for the same purpose, and we are also testing the effect of adding some ions and organic components to the medium using these particular catalysts. This is a list of the literature that we have started on our search for a good catalyst, and the work was started with a PhD student, Dr. Shayma Ali, an associate professor in the same department now, and also continued by Dr. Hagar Khalil, and Dr. Hagar now is a postdoc fellow at Ulm University, and we are continuing our work as well. And this is a picture of part of the group. The gentleman on the right side is not the only fellow male in the group. We have about 4 others who are now on the run somewhere worldwide. And in conclusion, let me show you an aerial view of Cairo University. And this picture was taken in the 30s from the first aviation test of the Egyptian airline. And at that time, as you can see, the landscape around here was full of green areas. And here is the picture nowadays. We have a lot of other buildings, and somewhere here, the Department of Chemistry is located, and you can see the traffic compared to the picture here. And this picture, I believe, was taken in the late 90s. Thank you very much.
Thank you so much. Thank you very much, Professor Ahmed. It's a great pleasure actually to have you here today. Interesting presentation, wonderful results, and I just got one quick question from Dr. Sudanshu. I think he's asking, I'm sorry, I don't know. Sorry about the mistake if I did. I have. She has one, or he has one question. Is barium titanium trioxide in nano composite always have high dielectric constant, or always to make high dielectric constant devices? The question is, I am working on this, but getting low dielectric at output. If this is allowed, this can be happen or not?
Yes, yes, I agree. I agree that dielectric properties are very much of the unique characteristic of these materials. However, it depends on the application that you are going to. No matter what, perovskites are now one of the key players in the manufacturing of the solar cells alternatives, and they are key players as for storages, for capacitors and batteries, and they are also now demonstrating their good candidacy as electrocatalysts. We have been working on that line, and we have seen that they can be many folds: sensors applications, catalysts applications. We have prepared one of the halide containing perovskites for the purpose of the application for solar cells. Now we are going to try also the photo catalytic activity of these materials while in the electrolysis mode, to see whether we can generate a better current and amount of hydrogen to be collected. But you are absolutely right. The dielectric constant is an important feature. Yes.
Uh, Thanks. Thank you so much, Professor Ahmed, for this great talk again. And I'm sure that if one has more questions, he can or she can contact Dr. Ahmed.
My pleasure. I will be around for the end of the session for any questions and to chat with the
Thank
colleagues
you.
and the wonderful
Unfortunately,
speakers.
this is the end of the session because Professor
Is that right?
Kenneth Oziumina from the University of Witwatersrand, Johannesburg in South Africa, he got COVID-19 while he was in China, and he's in quarantine now. So for 3 weeks, and he has very bad internet connection.
Okay.
So he
Poor Ken.
couldn't.
I hope that he will be recovering soon.
He's doing good
he's a
actually,
good
but
he's a
he's
good friend, and
yes, I know, I
and I
know.
wish for him I wish for him a good health
Thank,
and wealth and
thank,
safety for everybody, of course.
Thank you so much. Thank you so much. He was supposed to talk to us about the effects of carbon supports on the performance of palladium cerium oxide electrocatalysts for alkaline fuel cells. But I apologize on behalf of him to all the audience that he cannot give this presentation because of this emergency. And we hope to see him in future talks in Qatar University or Texas A&M University at Qatar. And I just like to remind you all that tomorrow's the biomaterial session will start at 9:30 a.m. in the morning. So please don't miss it. You know, we will have also a bunch of very good talks regarding biomaterials tomorrow. At the end, I'd like to thank you all for these wonderful presentations and for the audience for these nice questions and actually challenging questions in some cases. And really, I'd like to see you all in energy conversion sessions in future, in conferences related to the Emerging Materials Journal, which is sponsoring this event actually, which is published under Qatar University with collaboration with the Springer Nature. Thank you all.
Dr. Bakr, may I just say something quickly?
Sure.
If the presenters and the participants would allow me for a couple of minutes.
Sure.
Certainly, it was a wonderful conference, although online, but I think it covered a lot of interesting topics. But let me just mention one fact about Dr. Abu Bakr. I have had the pleasure of working with Dr. Abu Bakr in his early career. He gave me a lot of pleasure on cooperating and working and directing his first steps in the area of research. eventually I learned some of the important skills that he has shown during the short period I dealt with him in his early career before he moved to Penn State and many other places. So again, it was a great pleasure to see you again.
Thank you so much.
And to participate in the work and the conference you are organizing along with the other colleagues at Qatar University and Texas A&M, and thank you very much.
Thank you, Professor Ahmed. Actually, I had the honor and pleasure actually to be your first student actually after you came back from Cincinnati University, and I learned a lot actually, and still learning a lot from you. It's it's amazing actually relationship since 1993, and I have gained plenty of experience on the professional and personal levels from you. Thank you so much indeed for you and
Thank you.
for
I
everything
thank
you have
all the
done for me
speakers.
and
Thank you
for
very
others.
much.
Thank you so
A
much.
very interesting talks. Thank you very much.
Thank you. Thank you all, and see you tomorrow at 9:30 for the biomaterial session, and have a good night, everyone. Thank you. Bye-bye. Assalamu alaikum.
Thank you. Goodbye.
Assalamu alaikum.